The audio, I'm probably into headphone. Yes, I think. Yes. So. And 怎么办？有点小紧张，有点紧张。我原来也是一直都是 remote， 就是这种 offline 的第一次。Something wrong? Okay. And I think I'm over.
你要测声音吗？
声音的话，
声音往上。
就是一定要这个是吧？Okay, seems no problem. It's your turn. 你要说。
有 audio 吗？
有 audio。
audio 要只单独插。
哦，是吗 ？OK。它是。嗯，这个不能 extended 吗
？extended 可以啊，应该。应该是在回去。
就 display。
就 display， 我记得好像有一个选项来着 ，display setting。
Stop mirroring。OK。Cool。我试一下。OK。我试一下 audio。OK， 可以，就这样。好。
Hey,
It's going?
it's good. It's good.
Okay.
I'm testing the last one, the video. Can I just play the video using this laptop? I think it's okay.
Yeah, you would need to connect the
audio. And also
yeah. Are they dialing in via Zoom or so?
No, they are just like offline, and
Okay.
they will interact with the audience on Discord.
Okay, good. Yeah.
I just played the video.
Yeah, that's easiest. This is working? Yeah. Yeah, this one is for the recording, so you won't hear this one. But this one you will always hear.
So is that working?
That was the one on the rack.
Yeah, so that one is for the audience, right?
I didn't turn on.
Oh yeah. Yeah, that's for the audience. You can just hold it during the session and then.
Yeah, so we're gonna pass it to the audience.
Yeah, good. Yeah, perfect.
Thank you.
No worries. See if that is working.
I I should change
A
it all.
large part of the interactive display market.
Okay.
That's working.
That works.
Wait, can you keep it playing for a sec?
Yeah.
However, the simple act of touching on-screen targets actually involves complex visual motor coordination of the arm, wrist,
Okay,
hand.
good.
Okay. Thank you.
For people with upper body motor impairments, touch input brings about a variety of accessibility challenges, from raising the arm to landing the foot.
Okay, I will quickly check the other room and
Oh.
then.
Sounds good.
好，所以我等会主持也是用这个。
对，你就用这个。
OK。
或者不用你 PPT。对，他们要 Q&A，对，那你就得。
他们看，不是我主持。
对啊。不是，因为他们要 Q&A。
it's 9 a.m. now, so let's get started. So good morning everyone. Welcome to this session. This session is about accessibility. I'm the session chair Liang He. I'm from the Purdue University. Today we're going to have like 6 different interesting, great work presentations in this session. And also we have 2 best papers in this session, so it's going to be very exciting and a fun session. All right, so I'm very excited about that, right? So before that, I want to remind everyone to a couple of things. The first one, if you have questions, you can raise your hand. The SB will pass them back to you. And then we have a channel, Discord channel for each presentation. So if you have more questions, you can post your questions in those channels. Let's get started. So our first presenter is Qin Zhang. He's presenting Seeing Our Blind Spots, Smart Glasses-Based Simulation to Increase Design Students' Awareness of Visual Impairments. On behalf of his colleagues from Keio University, Goldsmiths, University of London, and the University of Tokyo. So Qin, take it away. You can set up the computer here.
Should I use my own adapter or use this one? Okay. By the way, can I take this thing off?
Oh yeah, you should take it.
It's okay. I can start? Yeah. Okay. Hello everyone, I'm Qin Zhang from Keio University. This work was done with Julia Barbarsky, Yifei Huang, Julin Li, Yunsun Pai, Jamie Award, Kai Kunze. To begin with, I would like to first introduce a short clip to have you to better understand what's going on of our device. So the main purpose behind this project, it's like, for example, when aging is still an unstoppable trend. So everyone like me, including me, here, it's very much likely to experience visual impaired syndrome sooner or later, or some of them may already experiencing some of those. So, but the problem is like our society is not prepared enough for those visual impaired people, for example, losing of central vision or peripheral vision. And so what if our main purpose here is to build a system that can like enable, especially for those designers, to build awareness of visual impairment people. And for example, use this system to check whether existing visual design is like a visual impairment people friendly or not. So to distinguish and to point out the difference among our study and those existing ones, we only choose some like latest one. For example, analog tools cannot chase the gaze movement, so they can offer like some static like visual impaired effects. But in the genuine scenario, the patient itself, like you can imagine, the eyeball it moves around, so analog tool cannot offer so. They are far from realistic simulations, but at the same time, VR-based methods can offer a fully modulated visual impaired experience. But you can tell, still like Kim et al., their system is far from realistic. It's like animation level, but when it comes to the latest one, like Crossos, it's a great work, but still, because there is like a video see-through based HMD. So what do you see? It's what do you say? What do you observe? It's indeed like a second-hand visual information. It's like degenerated from like a multi-channel visual information to just two-dimensional. So it's far from realistic. More recently, Crasso et al. Also built let's point out, let's clarify. Their method is video see-through. It's still like HMD based. They cannot access those like real world directly. But our methods, maybe, as far as I know, it may be the first optical see-through based VR AR glass to enable their users to access the real world directly. To point out the contribution among ours and those existing ones, for example, we have several roles to distinguish the contribution of our prototype. First, we can, unsurprisingly, to mimic central vision and peripheral vision loss. And then, since our prototype, it's like optical see-through, which means we have no constraint regarding resolution. So we are the highest resolution. So we also have eye tracking check. VAC stands for vergence accommodation conflicts, which is a main factor called motion sickness. So since it's optical see-through, you still have the gate steps to help you to figure out what's going on in the real world. So VAC-free check. Then weight. Our prototype is far lighter than any of those mainstream HMDs. And FOV, significantly wider, right? And then real-world adaptive, because it's optical see-through. You can quickly check what's going on, like just a switch on and off, the visual impaired effects to see if for example, I'm luckily a normal vision. I can see these details from this distance, but if I with this glass, it's super difficult for me to distinguish what's going on because the contrast was degenerated a lot. And then you can compare those two lines, red dash line and green lines. It's almost the same. It's slightly trivial, but in the following version, we may even increase this FOV to do our best to approach the widest FOV. Some may argue, what's the difference if we use those high-end, AR glasses, like HoloLens and Magic Leap? For example, to begin with, let's introduce HoloLens. HoloLens basically is using some additive. Additive, it means like RGB channel, RGB pixels. It's lightning. But our prototype is using monochrome transparent LCD, which means it generates black pixels. It reduces incoming light. It's totally different. It's more realistic if the purpose is to approaching degenerating like a macular degeneration something. And on the other hand, Magic Leap it is said to have some liquid shuttle in between the real world and the glass and the eye. But as far as I know, as the public information on the internet, the shutter can only be modulated by just 1 pixel. They only have 1 pixel, but our prototype have 128, multiple 128 pixels. Theoretically, we can manipulate whatever we want to do, to approaching each individual's difference. The hardware is quite straightforward. We use the well-used a pupil core as the base to track the user's gaze movement. And then we designed some extension kit, 3D printed its open source online. And anyone, if you wish, can replicate this demo for yourself without commercial use, please. And for example, if you're very familiar with pupil core, you may even notice these 2 arms. It's fully customized in case to have the best angle and the best position that enable us to track the eyeballs. Otherwise, because we realized pupil core, it's kind of friendly for some specific races, but it's not for me. It's not friendly for me like some typical Asian face, like lower nose and narrow or even wider head widths. But anyway, the logic flow is also straightforward. First, we have eye movement transmitted from those two infrared eye camera, see through the display towards the naked eye. And then we have the data, and then smoother data will be transferred to via USB cable to ESP32. Then we use those real-time data, generate some visual impaired effects towards those transparent LCD. And so to evaluate our demo if it really functions or it's just the imaginary, we have 3 types of tasks. One is personal item searching tasks, because the purpose behind this task is we want to approaching, if we can do our best approaching this real scenario, what's going on, to have impaired vision to search your personal item, the most familiar one. And to test visual acuity, unsurprisingly, this chat. And we have our own method to test the visual field test without using any fancy equipment of those eye doctors. To address if we can reach any changes in their awareness, especially for those design student awareness of visual impairment. So we have a baseline questionnaire beforehand. Then we do our eye calibration. It's okay. Then we have 2 main pathway. For example, participant can either follow this flow or this flow to finally reach post questionnaire, finally oral feedback recording. These are tips, because this Selenium chart is very used all over the world from over many countries. So there is still a chance that someone may tell the answer without actually observing what's going on. So we shuffled all those orders then, but we followed the original design, visual design, and those layouts. So this is the original one. You can tell the difference. It's brand new. But anyway, without any a surprising result, we reached a kind of good result. All participants faced reduced visual acuity kind of significantly. You can still see the answer like this plot shows. This is reduced peripheral vision, but we have 2 P4 and P8. P4 it's this person is kind of counterintuitive, but we lately figure out she was lazy eye. So because the display is too close, so he cannot help but one eye just doing so. So we reach this result. Otherwise, but P8 also indicate one of our prototype limitation, because the transparent LCD is used polarized film, which means you can see the generated effects at a very certain angle. Otherwise, some another angle, you can totally see through the generated effects. So in his case, no significant difference. But in the most cases, we reached a good result. And that is a questionnaire, and not much to mention. So you can find the details in our study. And we have MS1 and MS2, which stands for motion sickness symptoms. For example, when using VR headset, I experience headache and so visual fatigue, which is 2 typical symptoms for motion sickness we address. For example, in the MS question 1, they strongly agree they more or less experience visual fatigue or any kinds of motion sickness symptom syndrome in our case, but we do the great work regarding this reducing or even annihilate potential motion sickness. This is a genuine functional demo. You can see what's going on. For example, okay, let me adjust it. For example, these greenish like characters with those pinkish background, it's super difficult for people to see. But for the normal vision, we can still distinguish what's going on, what's written on this paper. But the problem is contrast is too low, spatial frequency is too high, so text information is undistinguishable. This personal item is still undistinguishable for this visually impaired person. However, on the other hand, what is visually impaired friendly design? It's like this way. Whatever covered, it's still distinguishable. Contrast is high, spatial frequency is low. Text information distinguishable because you can switch on and off to check if your design is good fit for those people in needs. Instant severity adjustment. To mimic those different level of visual impairments and limitations, wide FOV, universal design, lighter design, faster material, because you can already distinguish like the delay between the eye movement and those generated effects. I think that's it.
Okay, questions for Qing? And so you will pass the back.
Yeah, question.
Hi, Jen Minkoff, University of Washington. Thank you for presenting this work. The technology built looks really complex and interesting, and the motivation to support better design is certainly important. I wonder whether, I noticed that your study looked at how well you're simulating, but not how this translates into the way people make design decisions. And there's some literature right now that's sort of evolved in recent years that shows that simulation can actually cause people to develop unrealistic beliefs about what it's like to be blind or low vision, because the experience of immediate changes in vision is very different from living with them.
Yep.
I was wondering what your thoughts are about the limitations of the system and the future work that might need to be done to address those kinds of concerns.
Yes, to making sure to overcome those like significant difference among individuals, like those different pupil distance, and as well as to answer your question, one limitation is make it really workable. For example, when people lose their peripheral vision, this can be super dangerous because they cannot see what's going on here. They can easily hurt themselves. So this current system is also workable, but the problem is like it's wired. It have like extra PC attached, so it's not 100% workable. Like you just recommend like if you can make it more portable and workable to not only for those designer students and for those like people in needs, their families, to better distinguish what's going on of their loved ones and how harsh their real life is. So
I guess what I'm really questioning is whether people will incorrectly assume that real life is harsh with blind and low vision conditions, rather than understanding what it's like for somebody who lives with it, who has adapted their life to it and has a rich and successful set of techniques for addressing those kinds of visual changes.
by the way, can I have a personal question? If you are visually impaired person or not at all?
I am not visually impaired.
Yeah, as far as I know, like people losing their central vision, they can still doing their daily routines without obvious abstract, obvious like obstacle lies ahead. But when people losing their peripheral vision, their work can be super difficult. For example, I may like crash or even hurt someone else without my intention. But losing of central vision, it's nothing special, but can work and living as normally. And yeah, it's a good question. I will address like to collaborate with those experts in those specific field.
Okay, we have to move to the next talk. If you have more questions, just come to talk to Jing offline. And actually, Jing is on the market right now, so he's looking for the academic job. If you have some opportunities, you know who to talk. All right. So our next presenter is Xinyu Bruce Liu. He's presenting cross-ally identifying video accessibility issues via cross-model grounding on behalf of his colleagues from UCLA, Adobe Research, and UT Austin. So this paper receives the Best Paper Award. Congratulations, Bruce and others.
Oh, thank you.
Right, so is it ready?
Yeah, it's ready.
All right, take it away.
All right. Can you hear me? Wait, is it working? Oh, this one. Okay, sorry. So, good morning, everyone. My name is Bruce, and I'm a PhD student at UCLA. And today I'll be presenting our paper, Cross-Ally, Identifying Video Accessibility Issues via Cross-Modal Grounding. And this is a collaboration with my wonderful colleagues, Ruoling Wang, Bingzeyu Li, Anthony Chen, and Amy Powell. So many videos have accessibility problems that make the content visually inaccessible to blind visually impaired audiences. And to address the issues, people add audio descriptions to describe the important visuals. So for example, in this video, you'll see the host flips a pan over, but never described it.
First forming it over the back of the pan so it fits in easily. Remember to leave a little extra foil on the ends to create handles.
The host flips the pan over and puts the foil inside.
This step makes removing the cheesecake a breeze.
And in addition, videos can be auditorily inaccessible to deaf and hard of hearing audiences. And in this case, people will add closed captions that will describe the speech and non-speech sounds. For example, however, identifying video accessibility issues is challenging and time-consuming. Authors have to manually watch the video all the way through, playing and checking if the visual and audio information is accessible. And if not, they will have to describe it. And they often have to do this multiple times and watch the whole video multiple times. And this is especially hard for accessibility novices. So just going through all the videos. Most existing accessibility systems rely on using speech as a proxy for accessibility. So they assume that a video clip will be accessible if there's a synchronous line of narration, and accessibility issues occur when there are gaps in speech. But in our project, we find that speech is often not a good proxy for accessibility. So for example, many video types, such as vlogs, tutorials, and lectures, may not feature significant gaps in speech. And more importantly, the mere presence of speech does not mean that the clip will be accessible. So for example, in this video,
pretty quintessential millennial. I love contemporary art, I love glitch art, anything with the digital medium.
so in this example here, the author is talking about her favorite type of art. However, visually, she's showing a teddy bear on her bed. And the speech does not describe the visuals, so they are mismatched. In this case, people who cannot see the visual content will completely miss the information. To enable people to identify and address audio and visual accessibility issues more efficiently, we introduced Cross-Ally. Using a cross-modal grounding algorithm, Cross-Ally automatically locates visual and audio accessibility issues, allows authors to address accessibility issues using our interface, and creates a more accessible video from the authored descriptions. So the core idea of our system is to view accessibility as a modality asymmetry problem. As we've shown in the previous examples, a video may contain information that is only conveyed through the visual channel, or only through the audio channel. So those information will be inaccessible to people who cannot see or hear the content respectively. So therefore, our goal is to locate all those modality asymmetries in a video. To do that, we introduce a cross-modal grounding pipeline. So first, given a video, we'll split the audio and visual track and segment them into information bits. So in this case, we segment audio into sentences and non-speech segments and visuals into shots. Then we leverage a pre-trained multimodal machine learning model to compute the correspondence score for each audio and visual pair. So specifically, we'll map the audio and visual segments to a joint embedding space and compute their dot product. This will be representing how semantically similar the information is in both modalities. And after computing the scores for all audiovisual pairs, we'll have a correspondence matrix. So ideally, if the recipe video is really nicely described and well made, you should expect that everything on the diagonal line here should all have really high scores, because the visuals will be synchronously described by the speech and the audio will be synchronously captioned in the video. However, after plotting the correspondence matrix, we can immediately see that there are two columns here that are matched to nothing. So those visuals were never described in the video. And similarly, this row here is matched to nothing, meaning that that audio was never captioned or represented visually. Here is an example of a matrix of a YouTube video we computed using our pipeline, and you can pretty easily identify the unmatched segments. And in that way, we consider these segments as potential accessibility issues. So with the pipeline, we develop an interface to help people improve video accessibility. So this is our web interface, and the first thing you will notice is that on the bottom left, we have two timelines, just as our backend algorithm. There's an audio track and a visual track, and each track is divided into segments with different colors. So the level of redness here will represent the predicted accessibility of these segments. And users can simply click on the segments to quickly navigate through the video and especially navigate to the potential accessibility issues. Once users identify an issue, they can use the captions pane on the right and the video description pane to add a caption or an audio description for the corresponding segment. So for example, for this video, we see that the first audio segment is predicted as inaccessible, and we notice that it's background music that was never captioned. So we can simply type that to the corresponding text field. And then we find that, oh, there's in the visual track, there's an accessibility problem there. And we realize this is an action of flipping the pen over that was never described. So we can type the corresponding audio description. You can see that once we address the issue, the vertical sidebar and the corresponding timeline will turn to blue to signify that the issue is addressed. And as we all know that machine learning models are not 100% accurate. So if the model has a false positive or prediction error, we can simply dismiss it. And it will turn to gray. So this allows creators to make the final decision and review all issues. So the user's target here would be to eliminate all the red segments in those timelines and address all accessibility issues in the video. And finally, users can preview their captions and descriptions instantly with our interface.
So it fits in easily. Remember to leave a little extra foil on the ends to create handles.
The host flips the pad over and puts the foil inside.
So to validate the effectiveness of our pipeline, we conducted a technical evaluation. We randomly selected 20 videos covering a wide range of topics and manually labeled accessibility issues in those videos according to guidelines. And we used that as ground truth in our evaluation. We used the gaps in speech method as a baseline, and we found that for visual accessibility issues, although cross-highlight has a slightly lower precision compared to the gaps in speech approach, the recall score is significantly higher, jumping from around 30% to around 98%. So actually in this case, we prefer higher recall to high precision because we want to make sure that authors actually do not miss any information, any accessibility issues. And with our interface, as you've seen before, users can pretty easily inspect the issues and dismiss the ones that are already accessible. And for audio accessibility issues, our system had a higher precision and F1 score on our sample data. In addition, we conducted a user study with 11 participants. So we asked them to use both the gaps in speech interface and our cross-ally interface to make 4 different videos accessible. And participants' performance significantly improved. We observed around 40% increase in their precision recall of identifying both visual and audio accessibility issues. In addition, we observed that with cross-ally, participants felt significantly less mental demanding, the task was less difficult, and they felt less stressed and annoyed. And we also noticed that they were significantly more confident in identifying both audio and visual accessibility issues. We also ran more numerical comparisons with statistical analysis, so please read our paper for the full evaluation. And because of time, we will skip that and dive into the qualitative user feedback. So many participants mentioned that they employed a more dynamic workflow where they would still kind of skim through the gray segments, but paying more attention to the red parts. And this really helped them in a way that they don't have to pay attention to everything and be completely focused all the time. Participants also mentioned that deciding if the predictions are correct or not was so much easier than having to go over everything and look for potential issues. They can understand the issues in hindsight as soon as they see them. We also invited 2 expert content creators to use cross-ally to make their own videos accessible. So they expressed large interest in using our system and integrating our tool into their workflows. They said that seeing the issues, they would try to edit the video in a more accessible way and rethink how to structure the video better. So in future, we would like to explore incorporating cross-ally with existing systems that help people generate descriptions and captions. But our system focused on identifying the issue, we definitely see an opportunity to also provide feedbacks on the descriptions people write and the captions they created. In addition, we would like to apply our cross-modal grounding idea to other forms of content, such as text tutorials. And finally, we would like to explore how can we further incentivize accessibility for video authors overall by, for example, incorporating our systems into video editing softwares like Adobe Premiere Pro and Final Cut. As the content creator in our user study commented, your system should educate authors about what is accessibility and why it is important. Thank you so much for joining my presentation, and happy to take any questions. Oh, and you can try a live demo of our system here using the URL, or you can scan the QR code. Yeah.
Cool. So any questions for Bruce?
Hi, this is Venkatesh Potluri from the University of Washington. Really exciting work and great talk.
Yeah, thank you.
I was just curious if the visual content mattered at all. The reason why I asked is your teddy bear example got me thinking.
Yeah.
There's a lot of TikTok videos these days, for example, where you take audio from somewhere else and put a completely different visual.
Yeah.
So I was curious to hear your thoughts on how your system might perform for those kinds of content.
Yeah. That's a great question. So currently our system just detects all the mismatches between visual and audio, and I definitely see it to be a very important future work to incorporate the importance score, to predict the importance of visuals to users. So for example, in a tutorial video, the visuals might be more important than a vlog video or a random clip in a TikTok video, right? So yeah, I think we could do that through detecting the uniqueness of the visuals or algorithms like TF-IDF. Yeah.
Hi, I'm Kristen Williams from Emory University. First off, really cool talk, thank you.
Thank you.
I was wondering about your choice of identifying parts of the video that do not comply with compliance guidelines, basically, and that choice to use compliance as a cue towards accessibility. So there's research showing that oftentimes compliance isn't enough to ensure real access. And so I'm wondering, to what extent do you think this tool gives you a stepping stone to thinking through what real access might look like?
Yeah, so I feel like our system, sorry, are you talking about the data annotation process or the system?
Yeah, the idea that just both that you're targeting ground truth as compliance, and
Oh,
the
okay.
second that you're
Yeah.
using the data annotation based off.
Yeah, got it. So for the data set we created, we actually had 2 researchers go through all the videos and independently identify the video accessibility issues. So we have specific guidelines in our paper, and you should definitely take a look at that. And as for compliance, I feel like our tool provides more as I mentioned, a higher recall. So the target is to identify all potential issues, and once they are identified, it's really easy for users to address them and determine whether it should be covered or not. Yeah. Does that answer your question? Oh, okay. Yeah. 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 Oh, I see. Yeah. So for the guidelines, so for example, for visual accessibility issue, we label all the important visuals that is not described. So for example, actions, environment change, and text on screen, things like that. So we basically follow the ADB guidelines for that. And I'm not sure if I answered the second part, but I'm happy to talk to you later. Yeah, in more details. Yeah.
All right. So
thank you.
Yeah, let's thank the authors again. All right. So the next presenter, is Atash Mohag. He's presenting great coding, an accessible, efficient, and structured code paradigm for blind and low vision programmers. And he's presenting on behalf of his colleagues from Pennsylvania State University and Bangladesh University of Engineering and Technology. And this paper also received the Best Paper Award. Congratulations. All right, so take it away.
Thank you.
Table view. Table.
Okay, it works. Okay, hello everyone. Hello. Okay, all right. Good morning. My name is MD Hiteshamul Haq. Call me Hitesham. I'm excited to present our paper, Grid Coding, an accessible, efficient, and structured coding paradigm for blind and low vision programmers. My co-authors are Soyed Mustafa Mansour and my advisor, Soyed Masum Billah. This is my first time at UIST, so I'm very excited and at the same time a little bit nervous. Okay, so computer programming is mainly a cognitive task, and unlike many visual tasks like image editing or data visualization, programming is a text-based activity. So in principle, it can be done without any vision. But unfortunately, modern programming languages and environments or IDEs, they provide lots and lots of visual cues for sighted programmers. Here I have a 5-line Python code up here. So how many visual cues do you think you see here? What are the visual cues here? Okay, let's count. First, the colorful line numbers, then a visual gap between the line numbers and the code here. Also, the lines are visually separated. We have highlighted keywords like for, if. There is a particle line from line 2 to line 5 showing that this for statement and then this print statement, they are aligned. Also, there is this visual gap, or which we call indentation, in front of the if statement at line 3. So if I keep counting, I can go up to 13 visual cues in these 5 lines of Python code. Now, what if I remove these visual cues for you? This is how it looks like. And with a screen reader, I'll show you how it sounds, how the second line sounds for you.
2 space for space I space in space range left paren number right paren colon.
Okay, so this is not very helpful, right? And it can be difficult to understand for many people.
2 space for space I
Okay, so however, this is similar to the experience of blind and low vision programmers who use assistive technologies like screen readers to read and write code. Our contribution is grid coding, which addresses many of these problems. So first, let me show you how grid coding works. I'll start with this 6-line Python code and with most of the visual cues and convert it into the grid structure. First, we create 6 rows to separate these 6 code statements. Then we create the first column to represent the line numbers. We add another column to represent the global scope. Since this code snippet contains 2 nested levels, we create 2 additional columns and place the nested statements at their corresponding columns, like this. Now, indentations are no longer visual white spaces, but cells in the grid. So we add meaningful text like within if, within else for blind users, and bright colors for low vision programmers. Next, we add keyboard-only interaction and semantically meaningful icons to different grid cells. Assistive technology users can easily navigate our grid structure with 4 directional arrows. For example, I can use down arrow to go from row 1 level 1 to row 2 level 1. You can hear a visual cue that means that I'm going to a cell with a valid statement. A sound cue that means I'm going to a cell with a valid statement. Again, with down arrow, I can go to row 3 level 1. This is an indentation cell containing within if that tells me I have more content in the next level, so I have to go right. With the right arrow, I can go from level 1 to level 2 in the same row. Then again, with the right arrow, I can go to level 2 to level 3. So this time the sound was different, indicating that this cell is a padding to maintain the consistent structure. This is the maximum level, and if I press right again, I can hear a boundary indicator and stay in the same cell. So I'm not going out of the boundary. To facilitate rapid navigation, grid coding supports control with 4 directional arrows to jump over indentations or paddings. Let's say I'm at the else statement at row 5 level 1. I can use control and up arrow to go from row 5 level 1 to row 2 level 1 at the if statement, like this. And I'm skipping the within if indentation cells. Thus, we discretize the unconstrained 2D code space into constrained and structured rows and columns to facilitate non-visual navigation. Okay, now that you know the principles of grid coding, let me show how grid coding works in practice. Our prototype runs in a browser. It has many more features such as block like autocomplete, code compilation, and error correction. But for the interest of time, I only show you how to write a small code snippet with grid coding. Currently, the grid editor has only 1 row.
Table view, table, activate the cells, enter A.
User presses enter to edit.
1, 0. Enter, row 2, enter it.
And enter again to create the new row.
Down arrow, list, if block 1 of 3, enter.
Writing an if block with a suggestion.
Space, greater, space, 0, enter. Row 3 call P, R, I, N, T, left paren, tick, P, O, S, I, T, I, B, E, tick, right paren, escape.
Then presses escape to go to navigation and use the directional arrows to navigate.
Plus enter.
And finally, runs the code with alt enter. He goes to the code output to see the output. So that's how it works. The design of grid coding was informed by 28 blind and low vision participants. We adopted a participatory design and distributed our URL to 28 participants from 2 online forums. They experimented with our prototype for 2 months to improve our design. They provided us feedback like auditory cues, shortcuts, and different assistive features like rearranging the error message of Python. I cannot go into detail. Please read our paper for more design guidelines. So under the hood, grid coding has many moving components, but at the heart of it, we have something called the abstract syntax table, or ASTAB. It is an augmentation of the abstract syntax tree. Up here, I have a 3-line code snippet in Python, and on the right, I have the corresponding abstract syntax tree. Notice that abstract syntax tree is hierarchical, and for our design, we need a tabular structure containing the meta information such as statements, scopes, parents, and errors. So this is the ASTAB here that helps render the grid structure of the code snippet. And the conversion of abstract syntax tree to abstract syntax table is shown in arrows. Again, I'm not going into detail, but the first column comes from the tree, and the other columns are augmentation we created based on the tree. So we conducted a study with 12 blind and low vision programmers. It was a within subject study with 2 conditions: a plain text editor as the baseline, or condition 1, and the grid editor as the condition 2. We had 3 major tasks in our study. Task 1 is understanding the context or scope of a random statement. Task 2 is correcting common syntax errors. And task 3 is writing simple Python codes, for example, finding mean, max, or sum of a list. For the interest of time, I only explain 2 of the tasks. For task 1, context understanding, we ask participants what is the scope or level of a given line. For example, in the above code, participants needed to find out that at line 4, there is a print statement, which is inside a for block, which is inside another if block. We show 2 results here: the completion time and accuracy of finding context. On the left, x-axis indicate the task completion time in seconds, the less the better. The center dot indicates the mean or average completion time, and the 2 wings indicate the 95% confidence interval. From this graph, a participant took 80 seconds on average compared to 175 seconds of the baseline. In other words, participants are 54% faster in grid coding, and which had a large effect. On the right, the x-axis indicates the task accuracy in percentage. The more the better. Participants are 100% accurate in grid editor compared to 64% of the baseline. This result also had a significant effect. Overall, we found that the structure and the semantic information in the indentation cell was helpful for the participants to understand the context of the statement. For our code creation task, participants wrote a code in Python. An example task is given a list of numbers, add the positive numbers, and print the summation. We measured 3 metrics: completion time, accuracy, and completion time, number of indentation errors per block statements, and the number of non-indentation errors, which are syntax error except indentation, per block statements. Here I have the completion time on x-axis in seconds. The less the better. As you can see, participants took 125 seconds on average in grid editor compared to 136 seconds of the baseline. Participants are 8% faster in grid coding, which had a small effect. So this 8% reduction is not much, but we observed an interesting phenomenon for maintaining for writing syntax-free error code, syntax error-free code. Here I have 2 graphs here, the number of indentation errors on my left and number of non-indentation errors on my right. On the left, x-axis indicates the number of indentation errors per block statements. Less is better. Participants made 0.92 indentation errors per block in text editor. In grid editor, the number is 0.09, so only 1 participant made a indentation error, which is almost close to 0. So 90% fewer error compared to the baseline. This result had a large effect. Similarly, for non-indentation errors, on the right, the number is 0.29 with grid editor compared to 0.97 with text editor. So participants had 70% fewer errors in grid coding. So participants are able to write syntax error-free code in grid editor. there are many insights we learned from our study. There is one interesting insight. This participant said coding is like walking a road, and for a blind person, the road is dark, and errors are like falling down. Grid editor can give him the structure that he can hold on to, and as he is always aware of the structure and the position in the code, he can write more syntax error-free source code with grid editor. In conclusion, we present a source code in a 2D grid structure, and we found that it can help reduce comprehension, error correction, and creation times. Our editor is free and live. You can try it from the URL li-ide.herokuapp.com. Also, you can scan the QR code from the slide. Thank you, and I'm happy to take any questions.
We only have one question for this talk.
Hi, Meredith Ringgold Morris from Google Research. I was wondering, what's the largest size program that you used the grid code editor for, and could you talk more about the scalability?
Okay, yeah, so this is our like a new idea, so we tried with a small code snippet, probably around 30 to 35 lines. So this is our, like, to find out like how the structure works. With text editor, as you know that as the code gets bigger, it doesn't get like easier if there are more depths. So we believe that if we like increase the total number of codes, with grid editor, participant can still find the overall structure, like how many lines in the code, total, the overall number of levels, so that they can get okay, so this is like 100 lines code and probably 6 levels. So participants can still get an idea, like, okay, I have to deal with like 6 levels, or there is somewhere in the code there are 6 nested levels. So I can mentally prepare, okay, so I have to find out where the most difficult part is, or the most nested part is. So with like a bigger code, participants can get a better idea of like the overall code structure with grid editor.
All right, so Antash Mohak is also looking for industrial internships. So if you have openings, come to talk to him. All right, so thank you. All right, the next presenter is not here, so we are going to play the pre-recorded presentation video here. The paper is about interactive public displays and the wheelchair users between direct personal and indirect assisted interaction. The authors are Randu Daniel Fitevu, Ovidia Chiperin Anguran, Laura Bianca Billes from Stephen Zelmay, University of Saxiva. All right, so I'm going to set up here. And for this talk, the authors are not here, so they choose to interact with you, the audience, on Discord. So if you have questions, direct your question to the Discord channel.
A large part of the interactive display market is represented by touchscreen displays that enable simple and direct interaction. However, the simple act of touching on-screen targets actually involves complex visual motor coordination of the arm, wrist, hand, and fingers. For people with upper body motor impairments, touch input brings about a variety of accessibility challenges, from raising the arm to landing a finger on the screen to lifting the finger without sliding. For wheelchair users, parts of the screen may not be reachable from the wheelchair, or the pathway to reach the public display with the wheelchair may be little accessible. In this work, we address accessible interaction for wheelchair users and public ambient displays. In a first study, we conduct a systematic literature review and report very few scientific papers on this topic, with a preponderant focus on touch input and touch screens. In a second study, we conduct a systematic video review using YouTube and unveil accessibility challenges for public displays in several input modalities alternative to direct touch. In a third study, we conduct interviews with wheelchair users to understand their experience of interacting with public displays and preferences for more accessible input modalities. Based on the findings from these studies, we discussed two implications: the assisted interaction phase for public ambient displays and the ability dimension for cross-device input to support independent use of public displays via personal mobile devices. We conducted a systematic literature review on the topic of interactive public ambient displays and wheelchair users. After the identification, screening, and eligibility stages, we arrived at 20 scientific papers, from which 2 researchers extracted information about display setup, input modality, and accessibility challenges addressed in those papers. We found very little scientific examination of accessibility public displays for wheelchair users. Only a handful of papers describe prototypes of accessible displays, while the large majority briefly mentioned wheelchair users. We found a preponderant focus on touch input, while observations about accessibility challenges were scarce and brief. To find out more, we conducted a second study by running queries on YouTube to identify relevant videos, just like we used queries in our systematic literature review to identify scientific papers about public displays and wheelchair users. This time, we used a larger set of search terms describing motor impairments, health conditions, and types of public displays. After the identification, screening, and eligibility stages, we arrived at a set of 30 videos from which 2 researchers extracted information, just like in the previous study. We identified many mentions of accessibility challenges, which we grouped into 6 categories. The most frequent accessibility challenges were using touch input and reaching to content located too high on the display. We also identified new input modalities, such as touch implemented with assistive objects represented by a hand stick, a pen, or objects held with both hands, depending on the specific application and the health condition of the user. Not all of the videos contain dialogue, but when they did, we extracted and analyzed relevant quotes, such as the ones exemplified on this slide, that explicitly mention accessibility challenges, possible workarounds, or feelings resulting from the successful or unsuccessful use of interactive displays. To complete our findings, we conducted semi-structured interviews with 11 wheelchair users to understand perceptions about the experience of using interactive public displays and collect their preferences for more accessible input modalities. Most of our participants reported content located too high on the display, difficulty reaching the screen with the hand, and not enough room for the wheelchair in front of the public display as the most important accessibility challenges. We also found that assistance when using a public display that was not accessible was mostly provided by a companion. The highest preferences for input techniques alternative to touch input were for smartphone-based solutions, such as casting the screen of the public display to the smartphone or installing a dedicated smartphone app that would offer the same functionality as the display. We also found statistically significant correlations between participants' preferences for input modalities and their levels of disability and health measured with the HODAS instrument. Participants' comments provided further insights into the experience of interacting with a public display, such as reduced visibility from the wheelchair, perceptions of drawing unwanted attention, and avoiding using public displays because of sanitary concerns. The findings from our studies reveal the importance of providing assistance during interaction with public displays that are little or not accessible. The presence of an assistant means that 2 people interact with the public display to perform the same task, which depicts a use case not covered by Vogel and Balakrishna's 4-phase model. In such cases, assistance is provided by other people who also become users of the public display. We call this phase assisted interaction and show that it presents unique characteristics which open new research opportunities for public interactive displays. For instance, the secondary user that provides assistance to the primary wheelchair user can participate in interaction with the public display at various levels of engagement. They can help with a single operation, such as pressing a button located too high to reach comfortably from the wheelchair, which is a one-time assistance. The secondary user can continue from the point where the primary user left off, or can perform the entire task from the beginning during full assistance. These nuances in how assistance is provided have implications for the technical design of public displays that adapt to their users by observing the interaction, or that employ user profiles to customize subsequent interactions. Besides interactions with the public display, human-human interactions take place in the assisted interaction phase. The dialogue between the two users needs to be filtered out by displays implementing speech input or tracking users' head or eye gaze, which may get confused by orientations of the user's head not aimed at the display. Finally, there are privacy and security aspects when assistance is sought for interactions that involve confidential or sensible information. Overall, the assisted interaction phase addresses by design both situations where touch input in the public display is little or not accessible to wheelchair users. However, independent use of the display can be accommodated by alternative input modalities to direct touch, among which we found a high preference for smartphone-based solutions. This approach falls in the area of cross-device interaction since it involves a personal device and a public display. This slide shows how smartphone-based input for public displays can be characterized using the taxonomy of cross-device input as a synchronous one-to-m relationship between one user and multiple devices, fixed dynamics, etc. However, although using smartphones to interact with public displays has been largely addressed in the scientific literature, the resulting interaction techniques have targeted the average user. Moreover, the dimensions of the cross-device input taxonomy do not consider user-specific abilities to employ mobile devices, and thus they offer just a partial view on designing for users not possessing average but specific motor abilities. To complete this design space, we proposed a new dimension of ability to specify motor abilities expected from the user during cross-device interactions involving a mobile device and a public display. For smartphone-based input, this dimension specifies abilities required to operate a smartphone, such as holding the smartphone steadily during operation or touching targets accurately on the smartphone's screen. For this dimension, we suggest using a taxonomy of perceptual motor abilities proposed by Fleischmann in 1967 to describe motor skills in terms of general ability requirements in order to account for human performance on a wide range of tasks with a relatively small number of abilities. For instance, manual dexterity represents the ability to perform well-directed arm-hand movements needed to manipulate a smartphone and hold it steadily for interaction techniques that require pointing the smartphone to the public display. Aiming is the ability to perform accurate tapping on a surface, for example to select targets on the smartphone's touchscreen for technical solutions that involve installing a dedicated smartphone app that offers the same functionality as the public display. For more details regarding our studies and their practical implications for more accessible public interactive ambient displays for wheelchair users, please see our paper. Our findings revealed very few scientific publications on this topic, but we identified a diversity of accessibility challenges and opportunities to implement input modalities alternative to direct touch, which should be examined closely in future work. Thank you for watching.
Alright, so our next presenter is Pankaj Padaluri. He's presenting PSST, enabling blind or visually impaired developers to all the sonifications of streaming sensor data on behalf of his colleagues from the University of Washington and Microsoft Research.
Charge. Charge. Enter passcode. PowerPoint. Title text box. Text box. Psst. Voiceover off.
If this webcam will have really good audio when I do play the video.
Yes. Yeah, I'm just trying to test.
PSST was top V6 slide 11 slide 2. Star title. PSST was top V6. Voiceover on. PowerPoint. Title text box. Text box. Landscape. Portrait of Angel Lee. Woman smiling. Brown hair. Wearing sunglasses and white Lego branded t-shirt. Title text box. Text box. Title text box. Text box. Psst. Enabling blind or visually impaired developers. Small version
Sorry.
Control center. Media controls. Zoom. Not playing. From Zoom.
Yeah.
Playback destination. Button. Speakers and TV. Selected. Top. Speaker. Young History Pro number 2. Battery.
All right. Good morning, everyone. Thanks for waiting. I am Venkatesh Potluri from the University of Washington. I'm here and I'm very excited to present our work on PSST, a toolkit to enable blind or visually impaired developers to create sonifications of streaming data.
Title text box.
Uh-oh.
Title text box.
Sorry.
Control center. Media control. Playback destination. Button. Young History Pro number 2.
Okay, great. Before I jump into the talk, just an accessibility note that there are videos in this talk that contain some scrolling motion of the screen and screen reader audio and beeps that are generated by the toolkit. I will give heads ups before videos when they're happening, but in case I'm unable to give specific heads ups, just note that videos contain these cues. Great. Modern day, computing devices enable us to sense the environment around us and give us opportunities to interact with it in new and unique ways. For example, we do have thermostats right now which sense if we're at home and adjust the temperature accordingly. At the heart of creating all of these devices, or even understanding how sensors work, are microcontroller devices like the microbit, Arduino, and the Raspberry Pi. And these devices not only make learning about sensors more easily accessible, but they also enable us to create bespoke solutions that work for our own needs. However, a lot of the interfaces that these devices use to generate sensor data or display sensor data are very visual, and even in cases where they're not visual and they are like represented in a way that's accessible to screen readers, they're not very optimized for consumption by a screen reader user who is blind or visually impaired. To understand this, let's look at how a screen reader today announces data from a sensor on the JACDAC dashboard. JACDAC is a hardware protocol that is a microcontroller protocol that enables us to get data from sensors onto the web. So the video that I will play now is a screen reader speaking out values of the accelerometer on the JACDAC dashboard.
X, slider 0, 0.00399971, 0, minus 0.00399971, minus 0.00799942, 0, minus 0.00399971, 26 degrees C, device PP31 started, minus 0.0079.
So though the values are audible, it's hard to kind of understand what's really happening with that data. Is it increasing? Is it decreasing? How it's changing? And so on. With PSST, though, to address this gap, we designed and developed PSST, a data sonification toolkit that enables us to create data sonifications to understand sensor data. So let's quickly look at how PSST simplifies this experience of understanding sensor data. The video that I have here is of a microbit on a table with a light sensor, and as the flashlight is flashed onto it, PSST plays an audio tone that that informs us how the sensor is responding to the flashlight flashing on it. As the flashlight came closer, the frequency increased, and as the flashlight was taken away, the frequency decreased. And this not only kind of tells us that the sensor is responding to the flashlight, it also gives us a rough understanding of how the sensor is responding. To kind of understand how all of this works, I'd like to briefly introduce the key components of PSST. PSST is a toolkit that is built around the needs of physical computing developers who want to understand sensor data to work on physical computing devices. But we also test, so we have sensors, and data from these sensors is piped into data sinks. Data sinks are PSST components which take streaming data from a variety of sources. Yes, in this talk we're talking about sensors, but we've also tested PSST with static data and CSV files. Data from these data sinks then goes to data handlers. Data handlers are responsible for taking raw sensor data and converting it into ways that are more suitable to be presented accessibly. And these data handlers then send data to data outputs. Basically, the outputs are accessible ways of representing, and with PSST, we have a variety of them. We have the beep that you've just heard, which maps the data to a frequency. We also have handlers, outputs that play specific audio files to kind of set notifications. We also, PSST also supports speech to have specific values spoken, and we've also experimented with some data physicalization, which I'll talk more about in a bit. To see how PSST helps us better understand sensor data, let's try to understand how we can understand how a temperature and a humidity sensor respond when they're brought close to the mouth of a water bottle. The picture there is of a hand that is holding a temperature plus humidity sensor close to a bottle containing hot water. Note that PSST is a toolkit, which means developers can use it by invoking its APIs or and library. But we also built an accessible web-based dashboard that exposes PSST functionality to simplify its use, where developers can attach different handlers and outputs to sensor streams from JACDAC devices. So to get a sense of how a temperature and humidity responds, let's use the PSST dashboard. And first, let's attach a note handler to the temperature sensor and configure the note output of the note handler to play audio from the left speaker. What you will hear now is also what's kind of highlighted with this on screen. The screen reader in this video is basically verbalizing whatever is on screen so that you can add the handler.
Temperature PP31 and level 4. 23.8 degrees C. Menu button sub menu handler. No handler level 5. List of 13 sensors. No handler.
Great. Now, let's go ahead and add another note handler to the humidity sensor and configure its note output to play from the right speaker.
Control center.
Sorry.
Zoom. Not playing. Playback. Previous track. Playback destination. Button. Speaker. Selected. Dock connector. Living room. Home pod. Then code number 2. Battery.
Great. Now let's also try to get a sense of the exact temperature values. And to do this, let's add an extrema handler to the temperature sensor. The extrema handler is a handler in PSST that can be configured to report when the toolkit sees new minimum or maximum values in the data stream. And because we're bringing the temperature sensor closer to the water bottle, let's configure the extrema handler to play or to report data when it sees new maximum values, and then also attach it to a speech output so that we have the value spoken.
Is it playing? It's not. Say it again. Oh, sorry.
Oh, sorry.
What's... Nope, not playing.
Oh.
Let me try again. Do you want to back your video up instead of?
Yes.
Ready?
Yeah.
Humidity temperature TV 31 and level 4. 23.6 degrees. Minimum sub and handler. No handler 1 5. Filter range handler. Extreme handler 3 5.
Huh?
Your placement.
List of 13 sensors. No handler. But remove. Control stereo band. Clickable choose that. Choose data outputs. Checkbox checked.
Animation on clip 3. Slide 12 of 22. Animation on clip 11.
Extreme defined. Clickable combo box selects maximum.
Slide 13 of 22.
Maximum only.
Slide 14 of 22. Red dash box outlining the data block.
Combo box selects short.
Slide 12. Slide 11 of 22. Rewind. Animation on clip 3.
Checkbox checked. Speech.
Uh-oh. There seems to be something wrong with
Yeah,
this.
I have an idea, Venkatesh. Let me just move the projection over here,
Right.
and that way
Okay.
it'll be synced with me if I'm slightly off from you.
Right.
Sorry, folks.
Sorry, everyone.
Accessibility issues with the projector not having the proper audio support. Okay. Do you want me to play it again, or do you want to keep going?
We can maybe keep going.
Okay.
Yeah. I'm here.
Yes.
Great. So what happened is we also added an extrema handler and configured its speech output to announce values. Now, when we hit play, what we hear is two audio streams, like 2 different beeps increasing in frequency. Because of the AV systems, we might not be able to perceive the left and right stereo effect as much. However, I am happy to demonstrate that to you if you are able to find me in the hallways after the talk. And in addition to the speech, these 2 beeps, we will also hear PSST announcing the temperature values as they are increasing. Can you play that?
It's playing.
Oh.
Now there's no audio. Sorry, folks.
It's playing in mine, so maybe we could just put the mic.
You don't have audio either, because it's
Oh no,
on
I
your
can
phone.
remove it. That's fine.
So, hang on a second. You want to put the mic down to yours?
Sure.
Okay. And you're playing at the same
sec.
time as me?
Yeah.
1, 2, 3.
Animation on clip 4 again.
This not only gives us a sense of like the 2 audio streams, in addition to having the values spoken, we also get somewhat of a sense that okay, the temperature sensor probably has a more steady increase, whereas the humidity sensor has a more stepwise increase to data. So let's quickly look at how PSST made all of this possible. We have the temperature, and the humidity sensors that were connected to 2 different data sinks, and the data sync from the temperature sensor is then connected to a data output that is basically the audio output, and then the the data sync from the temperature sensor is connected to the node handler and an Extrema handler. The node handler here is responsible for taking the raw sensor values and converting it into a range that is, kind of pleasant to hear or like more audible. In PSST, we use what we call a MEL scale. And the Extrema handler, as I said, reports the new maximum values. And similarly, the humidity sensor also has the node handler. And finally, the speech and note outputs pipe the audio out, which is what we've heard when we pressed play. This is one example of how PSST helps us understand sensor data. We urge you to read our paper for a variety of applications and demonstrations of how PSST makes different types of data and more accessible. But another thing that we also explored, as I said, is some ideas around data physicalization, which what we did here is we built a handler output combo where we had, we could take the data and create an SVG that could then be laser cut onto a music sheet, which could then be piped through a music box to get a sense of, to just hear the data in a fun way. Just a note that there are more standard ways of generating tactile graphics, which definitely are possible, and definitely PSST, as I said, is a toolkit, can be extended to support those as well. But for now, let's try to hear how the data sounds when we pipe it through the music box.
Ready? Yes. 1, 2, 3. The video stopped.
Slide 17, slide 18 to 22. 2. Animation on clip 50.
This was interesting because the data, because the music sheet was laser cut, it also gave us a sense of like being able to feel how the data was kind of changing. So it was a quick way to get some rough representation of the data actually as well. To understand the impact of PSST on blind or visually impaired developers, we performed a study. And in the study, we first asked developers questions about their experience with programming physical computing devices, or in the case that they were not programming physical computing devices, we asked them for their experience about programming sensor-based apps. We asked them to help us understand how a few sensors worked using PSST. And finally, we had some questions to understand their overall experience. We request you to read our paper to get a full sense of the results, but in a brief summary is that PSST did give blind or visually impaired developers the tools that they wanted to kind of create their own data displays to understand sensor data, and it definitely sparked engagement and interest in wanting to do more physical computing. Taking a step back, really there's a lot of work in accessibility programming tools, and where there's like IDEs that are being made accessible, and we've just seen some really cool work on grid coding as well. And then there's also a lot of work in data visualization that looks at how we can enable blind or visually impaired people to consume data visualizations. And there's work in physical computing that uses a lot of visual modalities to make sensor understanding more easy for everybody. However, with PSST, we kind of look at this intersection of what does it mean for a blind or visually impaired developer to create their own data displays, and this is one of the few toolkits that support that, to kind of understand sensor data and think about physical computing. With that, just thank you to the many groups and organizations that made PSST happen. Make for All Group, which is our research group at the University of Washington, UW Create, which is an accessibility center, Google, Microsoft, and NSF as well. With that, happy to take questions, happy to give a live demonstration, and if you'd like to use PSST, please reach out to me at vpotluri@cs.washington.edu, and I'm happy to work with you to make sure we can work something out. Thank you.
All right, so I'd really like to have some time for questions, but we running out of time, so we have to move to the next presenters. But if you have more questions and want to see the demos, contact Tashi, and he is really happy to answer any kinds of questions. All right, so our last presenter for this session is Jiashen Li. He's presenting tangible grid, tangible web layout, designed for blind users on behalf of his colleagues from University of Maryland College Park.
Bracket, column length 3.
Thank you for Leon's. Hi everyone, my name is Jiashen from Small Artifacts Lab at the University of Maryland. Today I'm presenting tangible grid, tangible web layout design for blind users. This work collaborates with Ziyu Yan and Brahma Jaji, Ashley Shetty, and my advisor Hua Chupan. As you can see from the video, this work is about enable blind people to create web page layouts by themselves. So creating a web page or web page layout is pretty common to sighted people because they can easily change elements, colors, size, and locations. For blind people who want to design or maintain their own web pages by themselves, that will be more difficult and challenging because commonly used assistive technologies such as JAWS don't provide enough visual assessment to let blind people know where things are. So previous work have supported blind people to create web pages in different ways. For example, Code Talk and grid coding, which is just introduced, help blind developers to edit, debug, and understand the code structures which could be used in web development. But they didn't forget, they didn't focus on the understanding and designing a web page layout, which is a critical part of any web pages. So recent work such as the one done by Li et al. Through their system, blind people can use printed out tactile sheets to understand the web page layout and edit with a self-voicing tablet application. However, using tactile sheet or embossed paper need multiple step editing or printing. So our paper solves the problem that blind user could directly design and manipulate web page layouts with their hands and receive real-time feedback. So to fully understand the change of how blind people understand the web page layout and why blind people want to do it or not, we run a formative study with 6 blind participants. Fortunately, we have Brahma on our team, who is the co-author of the paper, and he is a blind developer who has a web page design experience. Here are some example questions we asked during the interview. Participants talk about their own experience and the pros or cons of existing tools. For those 3 participants who don't have any experience with the web design, we asked if they could understand the web page layout and how they consume web page information. We conduct the interview with each participant for about 45 minutes. So based on the feedback, we found 3 main challenges of blind people in understanding and designing a web page layout. First, current tools lack support for visual elements, so blind people can't understand the web page layout. A participant said, I could not do anything that is graphic. I can do my HTML, CSS, and put all the colors the way I learned it, but I don't know what is on the screen. Second, blind developers rely on screen readers to access the information on the screen. So audio feedback is primary, but not enough. Our participant mentioned, I can put the content in them with the help of screen readers, but I don't know how they are presented on a web page. And I always have to ask a sighted friend to confirm the result. So the third point, blind people desire autonomy, and they hope they can design a web page independently. Then, based on the feedback from the formative study, we decide on our design implications. First, the system should have a direct representation of the graphical layout. Second, adopting multimodal feedback to enable blind people has a better understanding of web page layout. Third, the system should support blind people design web page layouts independently. So General idea of this project is to use a tangible way to present the web page elements. Blind user can use tangible blocks to put them on a physical board to help them understand and design the web page layout. They can fill the block's type and location directly with their hands, and the system will provide real-time feedback. So to design the system, first we need to understand what kind of physical artifacts work with the blind users. For example, what size, shape, and mechanism can be used to represent layout information, and how that can be combined with audio feedback. To understand all this, we spent half a year and run multi-rounds of co-design sessions with Embrama. First, one key observation here is that all the graphical elements, for example, text, videos, images, and circle shapes are in rectangle blocks, but with different sizes. To represent these blocks of different sizes in tangible ways, we designed different shape-changing prototypes that test them with Embrama in one of the co-design activities. So here are 5 examples of rectangle blocks, including one with rubber bands, 2 with different telescopes, and 1 with scissor structure, and 1 with spring-loaded structure. We chose these designs because they vary with different rigidity of linkages. Some can maintain the shape, and others can go back to the original shape. The goal here is to understand what structure can help blind people understand and create blocks. So during the co-design activities, we asked Embrama to change block size and place them in different locations on the physical board and comment on difference. So finally, the scissor structure is the final design picked by Embrama for its rigid border, and it can maintain a rectangle shape while changing the size. Next, similarly, we also designed different types of physical board to represent the web canvas. And like before, we asked Embrama to give us suggestions on different designs. The magnet with groove is the final design because it has a flat surface that can easily place the block, and the magnet can ensure the board is firmly connected with the blocks. We also designed a list of tactile markers with Embrama to represent the web elements. The first column using different shapes is a chosen design. Besides tangible representations, we also looked into audio feedback. For example, what information and speed will be sufficient for blind users to understand the layout of the web page. Considering of the time here, there are more details in the paper. So here is our final prototype. The baseboard has 12 columns and 16 rows. The tactile markers are at the top of the bracket, and there are 4 magnets underneath. When blind user brings a bracket of a particular content type and close to the baseboard, the magnet will firmly snap it to the baseboard and self-align to the grids. Then the baseboard sends its type, location, and size, and immediately speak out the information to users.
Figure bracket detected, location at 9.5, bracket row length 4, bracket column length 3.
The user can also adjust the size or location of the web element to pulling or pushing the corners of the correct responding bracket. The update information will be verticalized, and the screen will be updated automatically as well.
Text bracket detected, location at 5.9, bracket row length 3, bracket column length 8.
Finally, the blind user can place multiple brackets, and the correct responding HTML web elements is simultaneously rendered on the screen with a content template. Now we have tangible grid tools. We want to know whether the tangible grid can help blind people understand the web page layout and how blind people use the tool. We ran a user study with 10 blind participants in 2 sessions. In the first session, we wanted to evaluate how tangible grid may help participants understand the web page layout. We presented participants with a predefined web page layout template. Here is the pictures. We asked participants to report correct responding web page layout information, including bracket size, location, and type. In the second task, we investigated how tangible grid may allow blind users to build a web page layout by themselves. As the goal was not to understand and test blind participants' design and creativity, we decided to ask all participants to create an identical web page layout. In task 2, all participants were able to complete the web layout design task. We also collect Likert scale questions to quantify the result. The answer range is from 1 to 7. 1 is strongly disagree, and 7 is strongly agree. Participants stated that the prototype was easy to use and learn with a mean score of 6.5 and 5.5, and that they felt confident when creating a web page layout. Although the participants were able to create a web page layout and happy with the design in general, I do want to point out that certain features do not always go as expected. For example, what you can see here are two participants trying to put the same tangible bracket on the baseboard. Notice that the participant on the first row, he placed the bracket on the baseboard first and then adjust its size. But participant at the bottom row should change the size of the bracket first in the middle area and then place it on the baseboard. Because of the different ways of handling brackets, the magnet snapping feature affects them in different ways. So one group of participants preferred them because the magnet could help them place brackets easily and self-align to the grids. The other group of participants don't like that because they noted after they placed a bracket on the baseboard, the magnet force was too strong for them to adjust the bracket size. So this also reflects in the Likert scale questions, and this tells us that the system design is an iterative process, and there is more we can do to make the system tailored to more different users. So to improve this in the future work, we can use an adjustable electromagnet to improve the user experience so that user can change the force between the baseboard and the brackets. Also, in the future, we can embed tangible grid into existing online web design tools such as WordPress and Google site. Blind people may design or customize the web page layout through tangible grid and upload it to an online platform. They can enter the contents through the platform and then publish their web pages. Finally, we can also support responsive web pages layout design to make different layouts for computers, tablets, and mobile phones. And thank you for your coming, and that's all for my talk. I'm open to the questions. Thank you.
Okay, actually we are running out of time, so I think this is the end of the session. If you have questions for Jiaxian or the other presenters, you're free to come to the front. They will be staying here for a while. And okay, yeah, I think let's just give a thank you all the presenters, and again.
We present Tickle.
Thank you so much.
Oh, this is your adapter, right? Yeah. I'll just leave it up here. Okay. Yeah.
So, hi everyone, it is 11 o'clock, and because I know everything is running late in general, we are going to get started sharp now so that you can hopefully attend also the vision talks afterwards. My name is Jazz Brooks, and if you're in this room, which is Cascade A/J, you are likely here for UIST 2022's Mind and Body session. I'm quite excited to hear from the session's presenters. Their work spans the gamut from sleep planning optimization to haptics and learning to even affective interfaces for laughter. So before we jump into presentations, we have two lovely lightning talks from Richard Lee and Yudai Tanaka. These brief videos are part of the lightning talk program, giving young researchers and first-time UIST attendees a chance to introduce themselves. So go ahead.
Hi, my name is Richard Lee, and I'm excited to be introducing myself today. I'm a fourth-year PhD student at the University of Washington, where I'm advised by James Fogarty and Shwari Patel. In particular, I'm excited to be attending my first UIST this year as in person as a student volunteer. My research interests include designing, building, and deploying systems that leverage sensing and machine learning to enable interactive health monitoring experiences for more accurate and timely measurements. Examples of my work include building a device to enable liver disease patients to track their chronic conditions, developing mobile sonar algorithms to enable physical therapy patients to track their progress in a fitness regimen, and designing wearable sensors to help everyday users gain even more insight into their own daily activities. I'm really excited to be meeting you all in person and virtually. Let's chat soon. Thanks.
Hi, my name is UIST. I'm a PhD student at the University of Chicago, advised by Pedro Rhodes. In my research, I'm exploring how to engineer new haptic devices by intercepting our nervous system. This allows for unique benefits when compared to traditional mechanical haptics. For instance, last Kai, I presented electrical head actuation, a system that stimulates the user's neck muscle to actuate the head and guide where the user is facing. As we only stimulate the neck muscle, the system keeps the user's head free, so it can be used for many mobile applications, even outside of VR. This year, I'm demonstrating these two things, a paper that I co-authored with my colleague, Jun Nishida. It's a device that synchronizes two users' hand gestures for haptic learning. Please come and try our demo. I'm very excited to chat with you and learn more about your work. I'm also currently looking for an internship next summer. I wish you all a great conference.
So be sure to say hi to Richard and Yudai if you see them around. They're actually at the front right now. Also, Yudai has brought the DigiSync device here in the room, so feel free to try it out at the end of the session if you haven't done so yesterday during demos. We will now transition to our talks, starting with Jungwon Lee from the Pohang University of Science and Technology. She'll be presenting on Sleep Guru, a personalized sleep planning system. And a reminder to everyone, there will be a student volunteer that can bring microphones to you when you raise your hand during the Q&A session. Go ahead.
Thank you for the introduction. Hello everyone, I'm Jung Lee from Postech. Today I'm going to introduce our work, Sleep Guru, personalized sleep planning system for real-life actionability and negotiability. This work is done in collaboration with Seongnam Kim, Mingi Jeon, Hyojin Chu, Jaeun Lee, and our advisor In-Seok Kwang. What time shall I go to bed for healthy life, and how long shall we sleep? Many people already know typical answers for these questions. Average healthy adults are advised to go to bed regularly around 10 to 11 p.m. every day and consistently have 7 to 9 hours of sleep. These guidelines are popularly used in commercial sleep apps and sleepworks. So first, you can see many pieces of research and sleep apps that remind you of healthy sleep patterns. For example, this is my Google Desktop. It shows my previous sleep logs and reminds me that my sleep patterns were inconsistent and try to go to bed at consistent times. And there are other sleep recommendation works that help me find the sleep guidelines that most fit me. For example, Sleep Bandits help me find helpful behavior guidelines, such as wearing socks or avoiding caffeine before bedtime. In these previous works, guideline itself remains unchanged, and the recommendation is about how to follow them well. Failing to follow the guideline means you fail to self-regulate yourself. But we have our own professional duties, so there are times when we cannot follow such guidelines. For example, we have project or paper deadlines and meetings across time zones. We could even be shift workers. So there are times when we don't have a choice but to live non-standard life. Until now, we had to approximate ourselves to the standard guideline or just consider ourselves as loud liars and do nothing. That's because none of the previous works answered to this question. What if we cannot follow the standard guideline for compulsory reasons? Our work, Sleep Guru, tries to answer this question for the first time. So we claim that standard guideline assumes standard lifestyles, and non-standard lifestyle need non-standard guidelines. In this light, we propose Sleep Guru, a real-life actionable sleep planning system. In order to design non-standard guidelines, we need to investigate how the standard guideline was established and apply it to individualized guidelines. So the physiological principles of Sleep Guru. We investigated the process of failing sleepiness. Human sleepiness changes over time, and physiological literature reports that there are two bodily systems governing human sleepiness: circadian rhythm and homeostatic sleep drive. And by combining these processes, we can evaluate the sleep pressure, a quantified measure of sleepiness. The first process governing human sleepiness is circadian rhythm. It is governed by melatonin secretion, which follows the daily sunlight cycles of 24 hours. And the second one is homeostatic sleep drive. When you're awake and doing some physical activities, ATP, an energy-carrying molecule, breaks down and adenosine accumulated in result. So this adenosine concentration makes us feel physically fatigued when keep staying awake. Taking the difference between these two bodily systems, we can evaluate the sleep pressure, a quantified measure of sleepiness. In most cases, circadian rhythm hardly changes, so we can see that the sleep timings, which can effectively control the sleep pressure in our active time, becomes a standard sleep guideline. This is how the standard guideline was established. Now let's see how we design Sleep Guru. Here, if you sleep regularly for a good duration, sleep pressure will remain under a proper level. But there are many factors affecting your real-life sleep. Among them, you can see the things like genetic factors, which are constant and static factors. So once you have profiled the individuals, they do not change that much. On the other hand, your time constraints or physical state change dynamically. So your project deadlines, some kind of social constraints, or whether you did some intense exercise or not. But those factors change day by day or even multiple times a day. Fortunately, we can get these factors from commodity devices or applications. So when designing Sleep Guru, we mainly focused on these two factors. Now I'm going to describe how the overall Sleep Guru system works. So from the Google Calendar, we can get the user's time constraints. And from the Smart Band, we can get the user's sleep logs and heart rate logs and infer the user's physical state. Considering these real-life factors, Sleep Guru computes optimal sleep plans, which minimize your sleep pressure in your active time. And the system populates them back to the user's Google Calendar so that the user can easily check their sleep plans along with other schedules. So you may wonder how these optimal sleep plans are computed, so I will explain them briefly. Our goal is to find the optimal bedtimes and wake-up times that minimize sleep pressure during one's awake time. But there can be a problem when you consider only sleep pressure. So to minimize the daytime sleepiness, there is a trivial solution to make the person sleep as long as possible, allocating all the free time to sleep. This is not what we want. So we added sleep duration as a regularization term to the objective function. All the sleep duration within the target time range are summed into this SD term. Now we can find appropriate sleep timings that can effectively control our sleepiness in our active time with proper sleep duration. So next step is to reflect our real-life constraints. One hard constraint is that the sleep plans should not conflict with the user's existing schedules. So for all the calendar events, we can make a set of constraints by concatenating all the start points and end points of the schedules. And other factors such as effect of physical exercise, sleep phases, are also applied to our system as soft constraints so that the system can flexibly reflect them. And for more detailed explanation, please refer to our paper. And next is our system's dashboard interface. So in this way, Sleep Guru computed the optimal sleep timings and provided them to the users. But even with given recommendations, what should you do if your night experiment takes longer than you expected? Or you may wonder if the recommended sleep timings are really optimal. So we made our system explainable and negotiable with dashboard interface. Dashboard has two components. Sleepiness calculator allows you to test what if I sleep earlier or what if I wake up later. So by showing the expected sleepiness, it helps you get convinced that the recommended sleep recommendations are really optimal. And wake up time calculator lets you seek alternative sleep plans when you cannot follow the original recommendations. For example, it helps you find the answer to the question such as, when should I wake up if I had to delay my bedtime? It helps you follow the next best option, not just giving up when you have to fail to follow the original plan. So the system calculates alternative sleep plans along with the optimal sleep plans and shows them through the dashboard interface. Now the user studies and results from them. We conducted 3-stage user studies and finally deployed Sleep Guru to 20 students for 8 weeks. The first 2 weeks are for observation phase, and the following 6 weeks are for recommendation phase. To compare the user's impression and compliance with the standard guideline, we have included 2 weeks of standard recommendation in the deployment. And the participants submitted daily questionnaires 2 times a day about the sleep quality and daily sleepiness. We also conducted weekly interview and final exit interview with every participant. And here are the results. So we evaluated the participants' sleep quality by LSEQ measure, and the result shows that the sleep quality has improved by 15% in Sleep Guru compared to the observation phases. In sleep efficiency, the decline rate of sleep pressure was more than 5% faster than the observation phases. And we found that the overall sleepiness of middle of the day has decreased and also received some positive comments from the users. The compliance rate is about 3 times better than the standard recommendation phase, and we can get some comments from the interview that the participants felt respected when provided Sleep Guru's recommendation, because Sleep Guru's recommendation considers your real-life constraints and gives them some followable sleep plans. And dashboard interface also shows some positive effects, while there were some limitations. And discussion. Here are the limitations and possible future works of Sleep Guru. There are so many factors affecting human sleepiness, and many of which are unknown in even clinical literature. And it's hard to help people who have extremely packed schedules. And for the future works, we may apply individual factors and improve Sleep Guru with additional features, and so on. And here are the takeaways. Sleep Guru envisions harmonious coexistence of healthy sleep and individuals' diverse duties. In this slide, our first prototype computes hyper-personalized sleep plans free of In this slide, our prototype computes hyper-personalized sleep plans free of real-life constraints, optimizing over physiological models, upcoming schedules, and physical activities. And thank you for listening. I'll be very happy to take your questions.
So for the time, we have only 1 to 2 minutes for questions. We're probably going to take one to keep things going. Raise your hand and I'll bring the mic towards you if you have a question. If not, I have some pre-prepared. I'm going to let people think for a second. Oh, I see one.
Thank you for the presentation. My name is Hyung Go-jung from University of Seoul. I have two quick questions. My first question is, it seems that some schedule might need to be added on Google calendars. So I'm just curious. I wonder if how you might able to motivate people to add their schedule in advance. So that's my first question. My second question is, it seems that some information might people might need to trust such information from your system. So how do you have a thought or idea how you able to make people to trust information provided by such system?
Thank you for the question. And the first question was about how to make the users input their schedules to the calendar. Well, in our user studies, we made them input their schedules one by one, for all the schedules they have. But inputting all the schedules is not the goal of our system. So it's a little burdensome, as you know. So in the future, we think that the research is like automating some calendar items entry, like from your emails or your smartphones. So this can help our system sleep guru. And the second question was about
trust.
Trust. Well, for the trust, we made some this dashboard interface. And in this dashboard interface, you can see that some sleepiness difference, and you can see your sleepiness change with your real schedules. So you can see that these schedules are, for example, if you delay your bedtime, these schedules may conflict with your high sleepiness time. So you can be convinced that these recommendations are really optimal, and like that.
Thank you so much. And that's for Zhengyan. We're going to be moving on to Hongshan Chen. So let's see here. So next we have Hongshan Chen from the National SIGCHI University, presenting on RSO, a resistive force feedback interface.
Hi, I'm Hongshan Chen from National SIGCHI University, Taiwan. I'm going to share our work in LESO. Haptic feedback not only enhances immersion in VR, but also delivers expert haptic sensation tips in VR training. For various manipulations, we propose LESO to integrate resistive force and rotational resistive force with our result resilience in grasping and twisting. Take VR factory training for example. When grasping an elastic object, resistive force is perceived. And when clamping a tenant, the user feels resistive force without resilience, which means no resistive force applied to the hand when the user starts pushing. When turning a knob on the machine, rotational resistive force is perceived. When tightening a screw, the user feels rotational resistive force without resilience, which means no rotational resist force applies to the hand when the user stops rotating the screwdriver. Okay. Therefore, it also renders shapes as well as 4 resist force modes from 2x2 factors, resistive and rotational resist force with and without resilience. And it also combines exoskeleton, detachable rings, and elastic bands to render versatile resist force feedback. Here's the animation of our device of one finger. To achieve the goals, 3 features are leveraged in Elesto. First, exoskeleton and detachable ring design. And here's the exoskeleton part. Inspired by Desmond and Destrins, we utilize the ratchet and pull mechanism to break the exoskeleton for shape rendering. And furthermore, an elastic band is in a band track connected to a detachable ring. A motor control is lent to render various resist force levels based on our previous work, Elastic VR. And a servo motor controls the Tennant and Mortis mechanism to detach a ring to render resist force. And second, resilience break. The blue arrows are the force from the elastic bands, and the red ones are the resist force felt by the user. The left video is with resilience mode. And the resist force change as the fingers presses, which is the same as the force from the band. And however, in the right one, without resilience mode, when the user starts pressing, the resist force doesn't apply to the finger, which means the force from the band isn't delivered to the finger. Furthermore, when the user repeatedly presses, the resist force increases. And since the elastic band always accompanying resilience, we leverage a ratchet and pull design to build a one-direction resilience break to switch between with and without resilience modes. And in without resilience mode, it prevents the resilience from being delivered to the finger, but still allows resist force to be delivered to the finger if the band is further extended. And third, ring duration adjustment. For the twisting mode, the duration to detach the ring is adjusted. A servo motor rotates the ring, so that the device switches between grasping and twisting modes. And the cone case design, it guides the ring detachment direction. So the user has to rotate the finger in the corresponding direction to detach the ring and perceive rotational resist force. Okay. And in the twisting mode, the guiding ring is a fixed pulley. It guides the ring connected to the ring. It guides the line connecting to the ring smoothly. Okay. And to maintain the dexterity, Elesto provides 4 degrees of freedom for each finger, including the wrist MCP, PIP, and DIP joints. The horizontal degree of freedom in the MCP joints and wrist are not provided, because the horizontal degree of freedom may counteract the rotational resist force. Okay. And we perform a resist force measurement to obtain the relationships between the elastic band extension distance and elastic force in different band lengths. As swing constant is in the upper right. And a ascending study was conducted to understand users' distinguishability of resist force and rotational resist force with and without resilience. A total of 4 conditions separated. here's the result. There's a significant difference between with and without resilience. Participants believe that resilience was also a reference to difference among the stimuli. So without resilience, reduce the distinguishability. There's also a significant difference between resist force and rotational resist force. Most participants mentioned that the resist force was easier to identify than the rotational resist force. And then we conducted a VR experience study to observe that, compared with current methods, whether ELESO enhanced users' VR experience. And three feedback methods were compared in this study, including vibrotactile feedback, resist force, and ELESO. And for vibrotactile feedback, coin vibration motors were used. And for resist force, the ring duration adjustment and resilience brake were disabled. And we built a scene of a VR factory. A total of 8 tests from the 4 conditions, with the 2 force levels for each condition were designed. And the results are in the figure. We found that ELESO is significantly better than vibrotactile feedback and resist force in realism. And for resist force with resilience, participants commonly believe that they were grasping ELESO cubes, and the visual feedback matched the haptic feedback in resist force and ELESO. However, P4 mentioned that the level 2 force feedback felt too strong. And for resist force without resilience, 7 participants said that they could perceive the resist force when pressing the button and clamping the tendon and mortise joint, and feel no resilience when stopping moving the finger inward. And 2 participants suppose that the vibrotactile feedback was more realistic, since it feels like the friction feedback when pressing or clamping. Okay. For rotational resist force with resilience, 7 participants saw that they were turning the knobs in the real world and could clearly distinguish different force levels. And 11 participants saw that ELESO was more realistic than the resist force due to the force direction. However, 2 participants mentioned that the resist force provided by ELESO was too large for rotational resist force. And for rotational resist force without resilience, 8 participants agreed that feedback from ELESO matched their experience of tightening screws in the real world. However, 2 participants said that the feedback was not very obvious, so they had to perceive it carefully when performing the tests. Okay. And ELESO still has some limitations. The size of it is still bulky, and the break of exoskeleton sometimes are not lock firmly, since the 3D printing rich samples are eroded after a while, which could be improved by using other materials to fabricate the rich samples. And furthermore, one DF instead of 2 DF for the MCP joints and wrist provided by ELESO still limits the finger's movement. So in conclusion, we propose ELESO to integrate resist force and rotational resist force with or without resilience for grasping and twisting. And we measure versatile resist force with various spring constants. And a JND study was conducted to understand users' distinguishability of the 4 conditions. And finally, we performed a VR study to verify that ELESO significantly enhance the user's VR experience. Okay. And here's my presentation. Thank you for your attention.
for the great talk. I was just wondering, the system itself looks quite bulky, and I was wondering if your users had anything to say about that, particularly when using like multiple fingers and having multiple copies of that system for each finger. Like, did they experience any fatigue, or did they like, were they nervous about breaking the system when like moving too quickly, anything like that?
I'm sorry, can you repeat the question again?
I guess just to summarize, I was wondering, since there we go. Since the system looks pretty bulky, did the users have any complaints about the system feeling too heavy or feeling like they had to be careful as to not break it?
There's some female participants said that the size of the weight of the device to them is too heavy. Yeah, so they in the study doing the study they will feel the device heavy. Yeah.
We have time for one more question. Okay, I'll ask one really quickly. I was curious, do you have any imagined future miniaturizations of the system, or like areas you could probably slim off in size while keeping kind of like the same functionality?
Maybe we can try the carbon fiber to make to fabricate our device, so the check may be shorter. Yeah.
Okay, thank you very much, Chen. And for anyone who has more questions, there's Discord or afterwards. We're going to move on to our next presenter. We have Adinobu Niijima from NTT Corporation presenting on learning muscle synergies, or piano movements in this case. Thank you so much.
Okay, thank you. Hi, I am Adinobu Niijima from NTT Corporation. Today, I will introduce an electrical muscle stimulation-based system to improve muscle synergies for playing the C major scale on the piano. When playing the scale, the muscle coordination of the forearm and shoulder muscles is important to play all notes evenly for high-quality music. However, learning the muscle synergies is difficult for beginners because they are not aware of using the shoulder muscle while playing the scale. Therefore, we propose an EMS-based system to teach them how to improve their muscle synergies while playing scales by presenting EMS to the shoulder muscle. In the introduction, I will explain the motivation for this study. Our research question is, does electrical muscle stimulation help with motor learning of muscle activity? We assume the goal of piano playing is not just to produce a sound, but play a sound. In other words, we want to make beginners enabled to play beautiful sounds by practicing with EMS. In related work, there are a lot of studies using EMS for teaching fingering to play musical instruments. Compared with them, we focus on muscle activity. In our previous study, we proposed an EMS-based system to reduce muscle activity while playing the piano. And in this study, we propose another EMS-based system to improve muscle synergies to achieve good performance for playing scales. So, what is good performance for playing scales? One of the indicators is the evenness of all notes. Playing all notes evenly is a basic technique to improve the quality of music. Playing each note with the same duration and the same velocity indicates good performance. This is an example of our pilot study's results in the difference between a beginner and an expert regarding the evenness of the scale. The expert plays the scale almost evenly, but the beginner plays the scale unevenly. The standard deviations in velocity and duration were large, especially D, E, and F notes. What is the difference between the beginner and the expert? We focus on the sum under method. The sum under method is passing the sum under the palm before pressing F key with the sum. It is achieved by pressing or releasing keys and sliding the hand sideways simultaneously. Experts use the sum under method, but beginners did not. Then we analyze the difference from the point of view of muscle synergies. Muscle synergies represent which muscles are coordinated when multiple muscles are activated. We calculated the muscle synergies while playing scales by non-negative matrix factorization. As a result, 3 muscles are integrated into 2 muscle synergies. For example, synergy 1 consists of the flexor and deltoid muscles, and synergy 2 consists of the extensor and flexor muscles. We compare the difference in muscle synergies between the beginner and the expert. The results showed the weight of the deltoid muscle in spatial synergy was smaller for the beginner than for the expert. This means the beginner did not use the shoulder muscle while playing the scale. Therefore, the beginner could not use the sum under method appropriately and play the scale unevenly. Thus, we propose an EMS-based system to improve the muscle synergies for beginners to play scales evenly. The system consists of an electric piano, PC, microcomputer, function generator, and isolator. We use MIDI data of the electric piano as a trigger to apply EMS, so that we can apply EMS anywhere in a musical score. In this case, when a user presses the E key, EMS is applied to the deltoid muscle for 200 milliseconds. When EMS is applied to the deltoid muscle, the elbow is turned out involuntarily, so that the user can use the sum under method before pressing the F key. With this human-computer integration system, a user achieves the appropriate muscle synergies for the sum under method through the coordination of the voluntary activation of the flexor muscle and involuntary activation of the deltoid muscle in a coordinated manner. The peak of the shoulder muscle activation is at the sum under method, so the system can make beginners strongly aware of this peak in EMS. Then, we conducted a user study to validate our EMS-based system. The purpose of this user study is to evaluate the effectiveness in improving the muscle synergies and the evenness of all notes when playing the C major scale. We recruited 16 participants who had no experience with piano training. After screening to check their skills, 12 participants were divided into 2 groups. In an experimental group, 6 participants practiced with EMS. In a control group, 6 participants practiced without EMS. Here was the procedure. First, participants played the C major scale at 3 tempi without EMS as a pretest. After taking a rest for 10 minutes, they practiced the scale for 10 minutes. The experimental group used our EMS-based system and practiced with EMS. The control group practiced without EMS. In both groups, we also taught the sum under method orally, so that they were aware of using the sum under method for playing the scale. After the practice, they took rest for 10 minutes. And finally, they played the scale at 3 temp without EMS as post-test. And we compared the pre-test and post-test regarding the muscle synergies and the evenness of the scale. For analysis, we measured electromyography data for calculating muscle synergies and metadata for evaluating the evenness of the scale. In muscle synergies, we evaluated the weight for the deltoid muscle in spatial synergies because the weight was larger for experts than for beginners. So we evaluated the muscle synergies as improved if the weight for the deltoid muscle increased in the post-test. In evenness of scales, we evaluated the SDs of velocity and duration because the indicators were smaller for experts than beginners. So we evaluated the evenness as improved if the SDs of velocity and duration decreased. Here are the results regarding muscle synergies. The weight for the deltoid muscle in spatial synergies increased significantly under the post-test condition in both groups. Their spatial synergies become like those of the expert. We consider this due to the use of the deltoid muscle for the Samanda method because they did not use the Samanda method before practice and used it after practice. Here are the results of the improvement in the evenness of scales. Regarding within-group comparison, SDs of velocity and duration significantly decreased in the experimental group, and those did not in the control group. Regarding between-group comparison, the evenness of velocity was more improved in the experimental group than that in the control group. We also received feedback from participants, and all participants in the experimental group claimed that practicing with EMS clarified how they use their shoulders for the Samanda method. These results showed practicing with EMS was more effective in improving the evenness of scales. In conclusion, let me summarize the findings. There are some important findings from the user study. First, practicing with EMS shows some retention of the learning effect. This means that the participants were able to use the Samanda method by performing the appropriate muscle synergies after removing EMS. Second, by presenting EMS only to the shoulders, we succeed in making participants more aware of the coordinated movements. This means the pinpoint use of EMS can lead to changes in the muscle synergies and a positive impact on the whole performance. In conclusion, we present the EMS-based support system for beginners in learning appropriate muscle synergies of the forearm and shoulder muscles. By practicing with EMS, the muscle synergies changed like those for experts, and the evenness of velocity and duration improved. However, there are some limitations such as validation of how long the retention of the learning effect continues. Therefore, we will evaluate the retention of the learning effect with more participants in future work. Thank you for listening to my presentation.
Okay, we have time for one quick question. Please limit your question to one. Thanks for the presentation. I'm Songjae from POSTECH. So in the evaluation, the participants played the C major scales. So it seems like you developed a system for a beginner. So do you have any plans to extend for the intermediate piano players for inducing performance improvement when playing more faster and complex notes?
Yeah, thank you for your question. This system is for beginners to improve the basic technique, but this system can also use for experts for difficult technique, more complex technique to improve the technique. And yeah, the limitation of this system is the delay of EMS. It is about 100 milliseconds. So very quick music like jazz piano is maybe difficult. But most music is for more than 300 or 400 milliseconds for each note. So this system can use for the almost classic music.
Okay, thank you, Arinobu, for your great work. If anyone has any more questions, you can catch Arinobu later or go on the Discord. We're going to now move to our final speaker for the talks. We'll be hearing about a foot interface from Don Sanita Alvitigaran from the University of Auckland. So thank you, Don.
Hello, I'm Don Samita Alvidigala. I'm currently a postdoctoral fellow from University of New South Wales, Australia, Sydney. And this work I did along with Roger Boldu and Dennis Mathis and my supervisors Rangan Arakara back then when I was doing my PhD in Augmented Human Lab of University of Auckland. So in my PhD actually I was explored a lot of novel input-output interfaces for our food. And in this work I was using the high sensitivity of our foot to develop a novel tickling interface. So before do further, let's start this talk. So let's look at a little bit of concept behind this work. So there are two types of tickling basically. So the first one is nismesis. So it's not evoking laughter, but it's self-inducible. So if you try like slightly touch your arm, you can try now if you want. You will see you will feel some sort of a giggling, but it's not really evoking laughter. But that's not what we are interested. We were interested in this garglesis tickling, which is basically evoking laughter, but it's not self-inducible. So if you want to do like this, you can't really laugh. So it's not self-inducible. So this is, which means it's basically interpersonal. Someone else has to tickle us to evoke laughter. I'm sure at some point you have experienced this in your life. But in 1999, Harris and Christenfield showed that this is not only interpersonal, even a machine can tickle you. So it's a reflection for a heavier tickling. So they basically did a wizard of study and then showed that even a machine can tickle you to evoke laughter. So after that, people have tried a lot of tickling artifacts targeting different body locations, such as wrist, cheek, hand, arm, even our foot sole. However, none of these work have rigorously evaluated to see whether they can evoke laughter, because it's not very trivial to evoking laughter using a machine. And some of them were only doing nismesis tickling, which is just slight touching, so you feel that nismesis feeling. So we wanted to develop a tickling artifact for foot that can evoke laughter. So we looked at some of the prior work, and then Charles Darwin had done a lot of research on tickling. So according to him, there are several body locations that are extremely ticklish, and then our foot sole is one of those body locations. And one reason is it has high sensitive nerve receptors and microreceptors, as well as these pain receptors. So this could be the reason. So we selected feet. And then we wanted to design a customized PCB, because prior work have basically used these vibration motors, but they were not really successful in tickling to evoke laughter. So we used this magnetic levitation technology, and then we mounted a brush on top of a magnet, and then we basically recreate these similar movements to human tickling action. So we basically actuated this actuator in two patterns, straight and circular, with 3 frequencies. And then we wanted to identify what are the best locations of our foot to tickle to evoke laughter. So we identified these 12 anatomical locations, and we recruited 13 participants and asked them to sort of actuate these locations. We actuate these locations, and then after our study, we asked them to like sort of rate the ticklishness. Then by conducting this study, we identified 3 such locations that highly ticklish across males and females. We also wanted to identify what are the best tickling parameters to evoke laughter. So we again recruited another 14 participants and then tested 14 stimulations. And then we identified when we stimulate both foot with a circular pattern and with a frequency of 2.4 Hertz, we observed that participants rated very high ticklishness. Also, we observed their behavior, whether they are smiling, laughing, or twisting and wiggling. So according to that, we identified that the same tickling pattern, when they experienced the same tickling pattern, they were either laughing or having a voiceless smile. Some people also had like twisting and wiggling while laughing. So we selected that as our best pattern for tickling. Then we wanted to confirm whether this is actually works across many participants. So again, we recruited 12 new participants and asked them to experience these tickling patterns or tickling artifact, but they didn't know that they're going to be tickled. So we collected their skin conductance data. So we observed that their skin conductance was increased compared to the ground truth skin conductance level, and also we observed the number of skin conductance peaks have also increased compared to the ground truth skin conductance peak. So which means they have experienced some sort of an emotional arousal. And then when we asked them to rate the valence and arousal and stress, they rated a higher valence and a higher arousal and then a lower stress level while experiencing this device. And then we also observed their behavior. So similar to the previous study, on average, they were either laughing or having a voiceless smile. When we asked them to describe what they felt, they were using the exact same words. It was tickling, ticklish, we were having fun, we were laughing. So those are the words that they used to experience these stimulations. So then we wanted to show the possibility of a wearable tickling insole. So we basically took 3 such actuators and embedded those actuators into a flexible insole, and then it had like several layers. So at the bottom it has a flexible aluminum heat dissipation layer, and then another layer of embedding all these actuators and wires, and then we had several protective layers, including a flexible silicon layer and a flexible 3D printed NinjaFlex layer. And then we again gave this to a bunch of participants and asked them to experience it. So this is how they reacted. They were basically laughing and having some fun. And then we also wanted to derive some of applications for these artifacts. We looked at the feedback of our participants, and then we also looked at some of the prior work in this tickling domain. So we thought that this could be useful for remote playful interactions for couples, and then even for eliciting mirthful responses in 4D cinema. And then finally to create distractions to release stress, because some of the participants were mentioning they were having some distractive episodes when they were experiencing this stimulation pattern. So I want to show a small video. Looks like it doesn't play. Just give me 1 minute, I will try to play it. Maybe we can skip it.
You can open the video directly. You have time, you can maybe open the video.
Oh, okay, yeah.
We present Tickle Foot, a novel foot tickling mechanism that can evoke laughter by creating tickling sensations along.
I'll just reduce the quality a little bit. Sorry about that, the internet seems a little bit slow. Anyway, maybe you can look at it later. This video had about 180K views, so that's the most views that I got for my research videos in the internet. So you guys can watch it later. Yeah. So before conclusion, I want to show some of the future work that we want to do. So New Scientist UK did an article about this research recently. So for that article, some of the neuroscientists have given some of their comments. So according to them, they think such interfaces can be useful to identify some of the special functions of our brain, such as the predictive coding. So we think that these type of interfaces, not only for those fun type of things, but also you can use for real research in neuroscience and then psychology to sort of identify special things in our brain, what's happening in our brain. Yeah, that's all. Thank you so much. And yeah, I'm happy to take any questions. Thanks.
Okay. So any questions from the audience so far? If not, I have some of my own. Okay. So access to the foot's soul and tickling itself feels very intimate in nature, right? I'm just kind of curious, did any of the participants comment on this aspect or think about who was actuating the tickling? As in, does like the machine mediation help with that completely, or are they concerned about who might be like actually
it's a very good,
producing the tickling?
Very good question. So it's actually to make it pleasant and fun, you have to have some sort of a it has to be what you call is consensus tickling, or the person has to be known. So there should be a like special relationship, or not special. There should be actually at least a positive relationship. So when we conducted the study, we make sure that the experimenter was having a positive rapport before doing this, especially in the final study. The first and second study, the participants knew that they are going to have this experience, so they already had some sort of a positive rapport with us. But especially in the third study, we had to create that positive rapport before we go for the stimulation. So that's really important. Otherwise, this tickling might considered as not acceptable for some participants. So we had to make sure that we do that before doing the experiment. Yeah.
We have time for one more question. If not, I think we'll wrap it up there. Thank you so much, Don.
Thank you so much.
For anyone who's around, thank you for joining this session, and I encourage everyone to continue these conversations with the authors during downtime and Discord, for example. The vision talk will be streamed here and outside, and a reminder, you guys also in the back with DigitalSync if you want to try that. And the vision talk should be starting in 2 minutes. That gives everybody some time if they want to transfer to the other room. Thank you so much to our presenters, Jungwon, Hongxian, Ayunobu, and Don. That was great work. And
yeah, it's like keeping it simple.
Do you see a screen? So.
Yeah, I see a screen and.
Lift off, so just make sure that we can see.
Yeah, it's like. It's like I want to extend.
Yeah, we need to test all of them. Do you want to go next?
Sure, I can bring in a doctor.
Do you, Amber, would you mind if she borrows?
Yeah, for sure. Yeah.
Okay.
Yeah, I am more than happy to share. Stop mirroring. Okay, that looks better.
Calming me down.
That's always the goal. Good chill vibes. Okay. It's like, is it this way? Where is it going?
I didn't know that, so I don't know how I find that out.
Okay.
So yeah.
Did I unplug this? Because I have like HDMI.
Oh, yes. Just leave it up here, though. That's Amber's, so.
Oh, I'd like to double check my paper's name. I found that something different. Concept level. Yeah, this should be like concept annotated.
Concept annotated?
Yeah, yeah.
Is it wrong in the program or something?
I think so. No. No, it's, oh, yeah, it works.
Did it work? Okay.
But
perfect.
how should I like go to? Okay,
Perfect.
now it's
Yeah,
good.
thank you.
Adapter's already prepared.
Yeah, I think I'll do all of that. Oh, yeah, I'll just read them off when I'm introducing.
Oh, we got an adapter here. Sorry, let me not do mirroring. All right, cool. Yeah, should be good. Yep, sounds good.
Awesome.
Hey everyone, we're going to get started. Yeah, so welcome to the session on programming kits and libraries. My name's Amanda. I'm from Apple, a research engineer. And today we have some great papers going over different things about taking notes on code, notation programming, web automation synthesis, and lots of other exciting things. So we also have 2 honorable mention papers in this session, which is really exciting. So for questions, you can either come up to so for questions, we're just going to do the microphone, pass it around. So please just raise your hand. And for virtual participants, you can post in the Discord channel. And we'll also have time for maybe 1 or 2 questions after each 12-minute talk. And we'll start with a virtual lightning talk by Aidan Bai, who is an independent researcher. So we'll go ahead and start that lightning talk.
Hi everyone, I'm Aidan Bai. I'm an independent researcher who's not currently affiliated with any institution. My current research focuses on developer tools that can optimize web application performance. In the past year, I've been working on Million.js, a fast, compile-limited virtual DOM library that improves the performance of websites that use virtual DOM, like Facebook or Twitter. It achieves this by using a compiler to optimize the interactive content of web applications, ultimately reducing the amount of computation to determine user interface updates compared to runtime approaches. When benchmarked, my initial findings show that Million.js has a faster load and rendering speed compared to React.js, a user interface library that uses a runtime virtual DOM. Outside of research, I love scootering and exploring the streets of downtown Portland. I would love to chat with you if you have ongoing work or a vision in the web space. Thank you.
So first off today, we'll have Amber Horvath presenting using annotations for sense-making about code. The co-authors are Brad Myers, Andrew McBean, and Imtiaz Rahman. So we'll have Amber take it away.
Oh my gosh, those masks. Hi, I'm Amber Horvath, and I'm thrilled to be back in my home state presenting my work using annotations for sense-making about code done in collaboration with my amazing co-authors. Modern software engineering requires developers to keep track of many different types of information as they change code. Some of these information challenges include keeping track of questions, answers, and facts about unfamiliar code, keeping track of working task context, which may be interrupted, and remembering which code versions produce what outputs. And these are only some of the things that developers need to concern themselves with. Given all of this information to keep track of, developers employ a variety of strategies to sometimes limited success. This includes writing code comments, but given the developer's current tasks, some thoughts may not be appropriate as comments, and cleaning up inappropriate comments can be laborious. Some developers take notes on paper and reference these notes when sharing insights with other developers, but these notes lack the context of the source code, making them harder to fully recall. Other strategies, such as leaving open a file if the developer gets interrupted, often lack sufficient context to remind the developer fully of what they were actually doing. So given this identified need for information tracking support that avoids the complications of the previous strategies, such as cluttering the source code, while retaining the positive qualities of these approaches, such as being lightweight, we offer annotating as an approach for providing this note-taking need in context. Annotations are lightweight, easy to author, and ephemeral, and also make use of the context of the source code so they are easier to recall and can have additional functionality associated with them, which I'll discuss more. Annotations have a variety of advantages over code comments, including being able to be attached to an arbitrary range of code, while code comments are associated with at most one line. Annotations also never change the behavior of the code since they're not actually in the source, while editing or removing code comments can sometimes result in parsing errors. Annotations not modifying the source code has other benefits, including allowing the developer to annotate code that they do not have write access to, such as external libraries, not requiring cleanup prior to pushing edits to a version control system, and the annotations can be private to a developer as opposed to code comments in the source code that can be viewed by anyone. Note that we are not saying that code comments are not valuable. There are situations in which code comments are preferable to annotations, such as in the case of documentation where the code comments should persist indefinitely. We identified 6 types of information we sought to help individual programmers keep track of using annotations. These information types include open questions and hypotheses about code, given that annotations retain the context of the source code and allow for following up on as a developer finds an answer. Open to-do items where the annotation can contain details about the task and be attached to parts of the code the task is relevant to. And facts learned about code that are perhaps not appropriate as documentation, such as in the case of debugging where the fact about the behavior of the code is expected to change. We also expect with proper tooling support that annotations can serve more code-specific activities. For example, developers often create a working set of code patches of interest. These patches can be kept track of and associated with one another using annotations. Annotations can also help with keeping track of small localized changes that the developer may not want to keep track of using more heavyweight mechanisms. And the annotation can also be a place to store changing system output, where the outputs can be associated with these localized changes. Later in the talk, we will go into more detail about how these activities can be supported through annotation. So given this need for better tracking developers' information while retaining the context of the source code, and to explore our hypothesized activities that annotations may help with, we developed CatSci, a Visual Studio Code extension annotation tool. CatSci includes a variety of annotation features informed by prior work on what types of information developers need assistance with tracking when making sense of code. CatSci has its own dedicated pane in the VS Code user interface to emphasize that annotations are attached to but abstracted away from the developer's working context, similar to how other annotation systems have annotations appear in their own side panel. This screenshot shows the CatSci pane with 2 annotations in it. One of the most fundamental activities in CatSci is creating annotations. Making an annotation is kept lightweight and flexible. Developers just need to select some text, and then they can either use a keyboard shortcut, context menu item as shown on the slide, or use VS Code's command palette to tell CatSci that they are making an annotation. Next, the CatSci pane will open, if not already open and visible, and update with an editor in which the developer can add their annotation. In this example, the developer is wondering what this value C is. Once the annotation is published, it will appear in the CatSci pane and the annotated code will be highlighted in the editor. If the user hovers over the annotated code's location, called the code anchor in the editor, CatSci will append their annotation and a show annotation button to VS Code's regular hover text. Clicking on the show annotation button will scroll CatSci to that anchor's annotation. This is how a code anchor appears in the CatSci pane. CatSci will keep track of the code's location and content as the user edits, such that if the user changes the code anchor in CatSci will update with the new version of their code. The user can click on the code anchor in the CatSci pane to navigate to that location in the editor. Given the 6 types of information we wanted to help developers keep track of when making sense of code, we designed features in CatSci to help with each of these activities. To help developers keep track of their questions, we allow the developer to annotate some code. Once the developer has an answer to their question, they can reply to the annotation with their answer by clicking the speech bubble button in the top. In this case, a developer discovered that the A element is treated like a button, so they added that information to their annotation as a reply. We imagine these features may also help developers with their open to-do items, along with the ability to pin annotations. When an annotation is pinned, it will persist in a pinned annotation list at the top of the CatSci pane, so developers can keep track of their open action items. Pinned annotations also have a special keyboard shortcut, such that with a keystroke, a developer can navigate between each pinned annotation's code anchors. Annotations can also serve as a place to jot down facts that the developers learn about different parts of the code. If a fact a developer discovers would make sense as documentation for the code, developers can also export their annotation content as a code comment. To ease the burden of navigating in a large code base, developers can use annotations as navigational waypoints with their code anchors. As mentioned previously, pins can be used to cluster together important code anchors and navigate between them with a keystroke. Another way of creating this working set of code anchors is to use multiple anchors. In this case, the developer has 2 code anchors, and the second anchor was created to better contextualize their reply about the A tag. Oftentimes, developers will try out multiple versions of their code while implementing a change. In some cases, developers may want to revert to one of these versions, but reverting a whole change can be pretty cumbersome. To help developers manage these small code edits, CatSci keeps track of the annotated code by automatically creating an initial version of the code when it was annotated, and automatically saves a version when the user commits their code with Git. These versions can be seen in a carousel view by clicking the arrow button by the clock icon. Users can also save arbitrary versions of their code without having to use version control by creating a code snapshot. In this case, the user changes the A tag to a div to test whether that changes the behavior of their website. While testing some of these small changes, developers have reported a need for keeping track of what version of their code produced what output. We provide annotations as a place to store these outputs. Developers can either reply to their annotation with the output values or edit their code snapshots with the output that came from that version of the code, thereby leveraging the context. Building off our prior example, this developer annotates their output with a comment stating that changing the A tag to a div did not actually change the behavior of the code. Together, this set of features allows CatSci's annotations to track a variety of types of information. So in our creation of CatSci, we wanted annotating to feel lightweight and fit into a developer's workflow with minimal confusion or overhead. This means we wanted annotations to behave in a way that feels natural to developers and in line with other annotation tools, but given the highly mutable nature of code, this introduced some challenges. One of the key design challenges was what to do with an annotation when its corresponding code anchor in the editor was deleted. Different annotation systems do different things. Google Docs will delete the comment, while Overleaf will keep a reference to the location where that comment used to be. We chose to delete the annotation with the idea that we want to cut down on annotation clutter as much as possible. A similar key challenge is what to do when a code anchor is copied. Again, different annotation systems do different things. We chose to not copy the annotation with the same rationale. The less annotation clutter, the better. So in order to understand in what ways annotating with CatSci compared to traditional note-taking when making sense of code, we ran a small lab study. We had 2 conditions, an experimental condition where participants used CatSci and a control condition where participants used whatever strategy they normally use when understanding code. Participants were tasked with understanding and debugging a purposefully confusing code base that included a website with buggy implementations of the games Tetris and Snake. The screenshot shows the game implementations along with some of the bugs each game suffered from. Participants in the experimental condition fixed on average significantly more bugs than the control condition. To further explore these results, we explore what information developers chose to annotate, how they used that information, how they performed on the debugging task. So here we see the blue bars, which are the average number of annotations made per session by what information the annotation was used to track. In our qualitative coding, we found that CatSci users created more question annotations on average than any other type of annotation. They also created more questions than the control conditions, suggesting that the annotating metaphor worked for capturing these kinds of lightweight ephemeral questions. We saw the same trend for hypotheses, which are similar to questions. There were no hypotheses made in the control condition. CatSci users also successfully used their annotations to help them navigate the code base. So now comparing the CatSci condition to the control condition, we see that the types of artifacts the control condition made were artifacts encapsulate any item the control participants made to track information, differ from what the CatSci users made. The control condition commonly used their notes for keeping track of facts that they learned about the code base and their tasks, with participants commonly making to-do code comments. Participants in the experimental condition revisited their annotations more on average than the control condition, revisited their notes. And when participants revisited their annotations, participants commonly replied to themselves. They used replies as a place to follow up on the initial annotation content. This included answering their open questions, hypothesizing about how the code behaves given further tinkering, and they wrote more tasks related to the initial annotation that they wanted to complete. Experimental participants also deleted their annotations more often when they were done with a task or resolved an outstanding issue, similar to how other annotation systems work. Participants also use code anchors, pinning, and multi-anchoring to help them navigate through the code base. Participants use their annotations and notes in different ways between the conditions when debugging. Control participants sometimes made visual diagrams explaining how they wanted the output to look, and visuals of how that logic should flow. Notably, CATSI participants did not create similar annotations, suggesting that CATSI could be improved through supporting pasting in photos, for example. This is an example of one of the visual diagrams that the control participants made. A participant was working through how they wanted the snake to move over time given different inputs. So in our development and evaluation of CATSI, we found two promising themes of annotation systems that we hope to explore more. One such theme came out of a participant actually continuing to use CATSI after our study concluded. She found that CATSI was valuable as a space to externalize her thoughts and to capture and preserve this thought history. These information scraps are normally thrown away or not externalized at all, but with our annotation systems, we hope to make this information capturing easier and repurpose this information to useful pieces of documentation for later users, such as for showcasing this thought history and provenance and rationale behind the code. CATSI supports different activities such as versioning, output capturing, navigation, and note-taking, with all these activities encapsulated in a single system. In the long term, we view code comments and other code-related meta-information as a continuum that we believe annotation systems can support through using annotations as a unifying lightweight interaction metaphor. Thank you. If you have any questions, I would be happy to answer.
Hey there, I'm Dano, research engineer from Meta. I had this really great idea when I was listening to your talk. Have you thought about integrating this with code review workflows? Specifically, it'd be really cool if you could get comments from your colleagues right there in your IDE alongside via an annotation format.
Yeah, that's actually definitely one of the spaces more broadly that we want to explore is collaborative software engineering, where code review is obviously a huge aspect of that. Leveraging the context of the source code, being able to use anchors to point to different parts of the code that maybe are relevant or informing the review. I think there's a large design space that is ripe for exploration. So definitely interest in that, yeah.
And can we just use this today?
It's out there. It's on the VS Code extension store. Yeah, I would, if any of y'all want to check it out, would be happy to support that and help.
Sweet, thank you so much.
Take one more.
Hey. Hi, I'm Danny Mesh from Virginia Tech. So I guess I'm very interested in this in terms of the ability to use it for knowledge transfer.
Yeah.
So I guess I'm wondering in that type of setting, do you have any plans for doing any studies with that, or do you have any other ideas for other affordances that you might need to support kind of sharing annotations between people?
Yeah, that's another great question, another area that we're kind of in the middle of exploring. The broader goal of this kind of system is if we can capture and keep track of all this lightweight information, ideally it would be great to repurpose it into these kinds of more long-standing documents that can help inform later people what exactly happened in the development of this code beyond just purely version control, which is cumbersome to go through, doesn't really capture all these interesting intermediate stages, and doesn't always capture the actual design that really or the design documents or anything like that that actually contributed to this kind of larger scale picture. So yeah, I would love to do a field study or something where people are actually using it in the long term to kind of see what annotations people make over time and if they're actually useful to that second, third, fourth, nth user. So yeah. Both of these questions, 100% very much things that I'm excited about, so glad y'all are too.
Good, thank you.
Very exciting. Let's thank the speaker.
Hi everyone, my name is Ian Arajo, and today I'm going to be presenting work I did with Anthony Diarmas, Michael Roberts, Shrutarsi Basu, and Tapan Parikh. And I'm going to be talking at a fairly high level for this talk, so if you want specific details, I urge you to see the paper. So over the past decade, 3 technologies have been on the rise. Hardware with high fidelity pen-based input, computational notebooks, and AI and deep learning technology. And so for me, this begged the question, why not consider or reconsider pen-based coding environments? Now, of course, pen-based interfaces have a long history in HCI, going back to its earliest history. But in fact, even before its earliest history, the very first programming language was originally just a translation between handwritten mathematical notation and what was typable on an IBM typewriter at the time, which I show in prior work. Now, in the 21st century, we've had a long time to live with a typewritten paradigm of coding. And so in our minds, we might think that, serious coding is really about typing. Like we have these other things, but really, if you're talking about the experts, they know how to type code. And as I've shown in prior work, this is because of a long history where cultural values have arisen around what constitutes real programming in users' minds and what does not. So the early adoption of the typewriter for programming reinforced a division between the textual and the visual, the written and the drawn, and other associations such as the visual is for end users or novices and the textual is for experts. Now this division is slowly being fractured, but it's still there. So I thought, what if we built a system that purposely tried to dissolve these boundaries? What if writing code didn't always imply typing it? So this is an example of that system. It's just a Jupyter Notebook interface where you can open a drawing canvas inside your code, and you can tap or touch on the canvas to enter a full screen mode. There's a rudimentary toolbar to the left. You can draw what you want, and then you can click off the canvas to exit and continue on. So here I call a draw command. 2 things to note about this. This canvas is seen as an image. It's performing offline sketch recognition, which is harder than online. And this QCR function, it's not exactly a function. It's what we call an interpreter in the paper. And there's an AI component, there's a deep learning component which makes this possible. Beyond just recognizing sketches in line, though, is this notion we have of implicit cross-context references where typewritten variables can be referenced in the handwritten scope and vice versa. This is a fairly general interaction paradigm. This is what we would call a notational program. And so it begged the question, how do you evaluate something like this? Because it's pretty general. So we chose a task domain of quantum computing. This is for 3 major reasons. The first is that practitioners in quantum computing regularly translate between circuit diagrams and textual code already. The second, important for me, was that it's conceived as an expert practice. It's hard to construe this as only for artists or designers. And 3, a technical reason, gate names are just simple, so it makes the recognition task easier. We targeted 2 specific notational elements for representing abstractions in quantum circuits. The first is the slash wire, which is commonly used by practitioners to represent a wire bundle, so a bundle of n wires. Of course, you cannot draw n wires. And the second is recursive definition, which is much less common, but is particularly powerful from a programming perspective. So here a circuit is defined in terms of itself, and in our system, you can define a typewritten variable C and then use that letter in your handwritten definition. So we ran a usability study. There were 6 programming tasks, which I'll talk about in a moment. We had a post-survey and semi-structured interview. This is with 12 participants. They were given 2 hours and $30 in cash. Screening criteria, important to note. There was a prior knowledge in Python and Jupyter notebooks that participants had to have, but no prior knowledge in quantum computing, so it's novices. So I won't have enough time to go through all of this, but the tasks suffice to say that the tasks, some of them relate to actual quantum algorithms. And it built up to the sixth task, which uses all of these abstraction elements which I've talked about previously. So we have implicit cross-context references where you use a circuit, you define it in terms of itself, and then you also can use it in a later definition. So some highlights from this usability study. The majority of our participants were able to complete all tasks within 1.5 hours, and all completed tasks 1 through 5. This wasn't particularly surprising. Actually, I was surprised that they were even able, the majority was even able to do this, because task 6, as you see on the right, was particularly difficult. Nearly all participants found implicit cross-context references, this notion, intuitive to the extent that we actually had to press them on it in interviews. And shocking to us, 3 participants actually thought that inline drawing canvases were just a standard feature of Jupyter Notebooks that just shipped, with the library. And these are people who use Jupyter Notebooks. They just thought it was some shortcut. So what did an interaction generally look like? Participants, even though they were using the pen, they wanted to touch the screen a lot more compared to a typewritten condition, which I'll talk about briefly. Some participants would draw in scratch paper, which we gave them, and then transfer their drawings into the drawing canvas later. Of course, users could encounter syntax errors, so errors where the recognizer actually did its job, but the users misunderstood the notation or made a mistake. And in this case, there was some kind of like type error, and then they would go in and they would amend their drawing. And then there were also AI recognition errors much more commonly. And in the best case, it would print a kind of plot like this, which users could then view this plot and then try to correct their drawing. But probably more commonly, the AI would think that it had recognized the circuit correctly, but then it did not, which led to numerous confusions, which we talk about in our paper. We also asked participants, whether they thought what they were doing was programming. And consistent with what I suggested in the introduction, they did not, most of them. This participant sums it up. She says, this is definitely less coding, it was more drawing. For me, coding is actually like writing out, I guess, like actually typing it up. This reveals directly that coding in this participant's mind excludes drawing, and writing actually means typing. So we also performed a comparison with a typewritten API. So there's evidence for and against our new paradigm, and there was also extremely high variance in tasks involving recursion. I won't have enough time to get into the details here, but suffice to say that it supports a heterogeneous vision of coding, where sometimes it's better to handwrite and sometimes to type, but it also underscored challenges, long-standing challenges at least, of comparing an established paradigm with a new one. So in conclusion, I hope you found this work just mildly interesting. And there might be many different things that you took from it, but one question that I always get to sort of preempt the Q&A is that, this is all right, Ian, this is all cool and all, but why didn't you just use a domain-specific GUI? Right? Wouldn't your usability study have been way better? Like, users would have loved it more, and you could have walked away, everyone could walk away much happier. And they used to, people would rattle off a bunch of things of why. And all of these things, I should say, and we also say this in the paper, I totally agree with, right? It would have been great for a usability study. But there's one thing that you can't do with a GUI, and I'd like to show you that now. So this is task 2. So basically in this task, participants just had to redraw this circuit as you see here. It's one of the first tasks they encounter. They just need to open a drawing canvas and redraw it. But actually, in order to solve this task, what participants could have done, what no one did, but what they could have done, is just right-clicked on this image here, copied it, and pasted it in, and then run the cell. And as you can see, it's the expected output. So you could take a lot of things away from this talk, but at its most basic level, what I think our paper is saying is, hey, we should just be able to use images in our lines of code. Like, it's the 21st century. And hey, look what cool interactions and like kind of creative interactions might emerge if just that much was changed about our coding practice. Not even speaking yet of domain-specific GUIs or VR or anything like that, but literally just copying and pasting images inside code. So thank you. I'd like to thank again my co-authors, and I am on the job market, so let's chat if you're interested. Thank you.
So let's take some questions.
Hi, Jasper Tranality from the University of Washington. Super cool talk. I love seeing computational notebooks being used in unexpected ways. One thing, so I noticed that sketching was a large focus of this talk, and implicitly also so was recognition. Like when somebody drew a circuit, we depended on AI to recognize symbols, and so you could also think like, what if instead of a sketching interface, it was like a drag and drop interface for creating these circuits? And so I was curious if you could comment, like, what is it about sketching that would be different from maybe like an alternative way of an alternative non-textual way of building these embedded circuit diagrams?
Do you ask the GUI question?
Well, not a GUI, but just not sketching. I guess still within a code environment.
Yeah, so that's what I would consider as like a drag and drop domain-specific GUI, right? I think, you know, you can consider that. I think one of the things I was trying to show in the previous slide is that that's one thing you can't do with a drag and drop GUI because it depends upon you making the thing within the context or bringing it in some way. You need to actually use the interaction. You can't like take a photo of a sketch you made and then just put it in the code. But you're right. I mean, I think actually these things could work well in concert, right? So if we had the ability to easily build these kind of interpreters, right, and then have some kind of drag and drop or some kind of editor that goes along with it to sort of support both interactions, that would be beneficial to me. I think the other example, which I wasn't able to, the other answer, which I wasn't able to actually put in the talk, unfortunately, was that I wasn't trying to do user-centered design. And I thought this was going to be like too much to like go off on a tangent about why I'm doing ontological design and not, you know, and I have to like define what ontological design is and whatever. But I guess the goal was to try to challenge users' existing practices. And for me, a kind of drag and drop GUI still uses the keyboard and the mouse clicking interface that a lot of people are comfortable with. So it was more of like a kind of critical design, if you will. But yeah, it would be very important to explore that avenue in the future.
Thank you.
Do we have one more?
Hi, I'm Kwong from Adobe Research. Very thought-provoking. So one thing I'm seeing is, you know, the problem of taking an image and turn that into code is very similar to a lot of layout problem that has been explored in the past. And, you know, quantum computing, the problem you're exporting right now, it seems to me like another example of layout problem. So it got me thinking, have you thought about how this framework could be extended to other problem, maybe like something with temporal domain in it, maybe like for interaction, games, animation, for example. Would this framework be extended to those programs as well?
Yeah, it's a great question. Yeah, that's what I hope to explore next, something that deals with notation and more interactive as well. Yeah, I still don't know exactly how to articulate what it is, but yeah, that's definitely something that's worthwhile exploring. Even within this paradigm, I think there's a lot of exploration for different domains. Of course, the challenge of doing this is always you have to build the interpreter, which is which can be a particular challenge. So, you know, and rebuild the interpreter many, many times. And so I would also be interested in exploring tools for making it easier to build such interpreters to begin with.
Awesome. I think that's all we have time for. I had one more thing. This paper received honorable mention Best Paper Award, so I wanted to hand this to Ian. Congratulations.
Thank you.
So next up, we'll have Kevin Poole presenting Semantic On, specifying content-based semantic conditions for web automation programs. The authors are Kevin Poole, Rainy Food, Rui Dong, Jingyu Wang, Yan Chen, and Toby Grossman. So.
All right, sounds good. Thank you for the introduction. Hi, my name is Kevin Poole from the University of Toronto, and today I'm here to present the work Semantic On, specifying content-based semantic conditions for web automation programs. And this work is done together with my co-authors, Rainy Fu, Ray Dong, Xinyu Wang, and my mentors, Yan Chen and Toby Grossman. So I want to start off by talking about data scraping, which is the task of extracting information from the web in an organized way to conduct analysis for different purposes. And this is very prevalent for companies, government, school, and researchers to gather a large amount of data. But at the end user level, imagine if you're someone who wants to download a large number of images, maybe from this photo gallery online, or scraping text from this book list, you would probably write your own web crawler via coding. Existing tools allow users to write their own scripts using domain-specific language or declarative programming, which provides a level of abstraction. And there are research tools where they use programming by demonstration systems to record and replay web macro actions, which further lowers the barriers for the users. However, there isn't really a way to specify semantic conditions based on the content. If we take a look at this photo where it's a portrait of interaction between two people, it is very hard for users to, specify that they want to download images based on a. And similarly, if someone wants to scrape text based on the main idea or key entities present in this passage, for example, finding book based on the plot or specific settings that go beyond just genres, it is very hard for the users to express such conditions. Through analysis of previous web automation tools, as well as online posts in web scraping communities, such as iMacros Forum and Stack Overflow, we identified two central needs. One is the need for conditional web scraping, as seen by this quote here from a participant in the previous study, where they desired a conditional web scraping that goes beyond syntax and structure, as well as semantic high-level understanding of the content. So one request that we encountered was that someone wants to scrape Wikipedia data on US presidents based on their family composition and education status, which goes beyond simple syntactic and structural similarities. With the current approaches and current tools, if we want to achieve that, the users will have to scrape all of the candidate images or texts in data scraping, and then filter the content in post hoc processing, which is time-consuming and not very scalable. So to fill this gap, we introduce our system Semantic On, where users can follow this three-step approach. They can first specify semantic conditions on the content via two methods, prompt or content highlighting. Then they can create automation programs from web macro demonstrations. And at last, as the program continuously executes and automates, the user can refine the conditions and repair any system errors at any point. To briefly talk about the system architecture, the user follows the white arrow in this workflow, where they first specify semantic conditions on example contents, and this will allow them to leverage image recognition models, as well as semantic text comparison models to parse and create filters for visual and textual content. And for the second step, the user demonstrates their desired action on the website, which are recorded by our program synthesizer, WebRobot, which generates automation scripts based on the user's web macros, as well as the website structure. And as the program is synthesized and executes, users can reclaim control at any point to refine the conditions and repair errors. This way, Semantic On combines program synthesis and machine learning techniques to build a continuous human-AI collaboration. And I'll show you what this means with a demo. Oh, let me see if I can. Yep, okay. All right, so for this example, let's imagine a photographer who wants to do some research on group portraits. They launch SemanticCon via the Chrome extension, and maybe for this specific task, they want to download photos that captures moments of interaction between a few people. To specify that, as you saw, they can use user enters, which is simply typing in a intent in her own words. They click on the image to set a condition on and writes a few people interacting with each other and adds the condition to our panel. Alternatively, they can specify this condition using system suggests. In this mode, the user again clicks on the image, but this time they use the mouse as a brush to highlight an area of interest. Then SemanticCon detects the objects and generates a caption for this image. User can highlight the relevant tags and add them to the condition table. This interaction alleviates users' mental effort of summarizing their own conditions and helps them to understand the system's interpretation. So after defining a set of conditions, the user can click Start Recording to demonstrate their intended action on the website. They can enter a task name as well as the number of columns. And since in this task they want to download photos, they select Download Image and click on the first couple of images. And just after 2 rounds of demonstrations, SemanticCon predicts the next intended action and enters a semi-automation mode, guiding the users through each piece of information, asking for confirmation or rejection. The user might find that the person condition is too general as it matches with this picture of a crowd, which is not what they want. So they could delete the condition as well as the result. And for this ambiguous photo, the user might decide that the 2 people are not really interacting with each other, so they agree with the system to exclude it. The skyscraper image is excluded correctly. And for this photo, even though it doesn't match with any current conditions, the user can append a description to the condition table as it goes. So after a few rounds, the user might feel confident about the SemanticCon's automation, so they can click Hide Prompt to fully automate the program. I see on the top left. So this will get rid of all of the pop-ups and enters full automation. But once they spot an error, for example, on this previous image, the system did not actually download it, even though it is 2 people interacting, they can pause the program and come back to manually repair the error. They can also inspect the detection results by clicking on the information icon in the bottom left. Through this continuous collaboration, the users can specify and refine the conditions on image content and create an automation program without writing any code. They can also reclaim manual control at any point to repair the system mistakes. This real-time conditional web scraping increases scalability as it does not extract any irrelevant information. In this demo, similarly, the user can create semantic conditions for texts. Take this book list, for example. The user can specify a main idea using user enters. In this case, they might be looking for romance novels that involve a female protagonist that goes through life's ups and downs. Or they can highlight a passage to extract key entities using system suggests. After demonstrations, the user again successfully creates a text scraping automation program. And in this final demo, the user can combine text and image conditions as well. This case, we're considering a traveler who's collecting text descriptions as well as images for their ideal travel destinations. They can perhaps set conditions on the text. In this case, they might be looking for outdoor activities. They can highlight sentences that involve hiking trails or kayaking and so on. Or they can highlight images to indicate their interest in traveling to somewhere with both a mountain view as well as bodies of water. Together, the user can create automation with multiple columns of text and image data. And at last, if we focus on, sorry, a little bit ahead of time. Yep, if we move our focus to the top left with the logic switch, the user can toggle the logic switch between and or to connect or combine all of the conditions differently depending on the task requirement. So that is what the system looks like in action. To evaluate our system, we ran an in-person user study with 10 participants. And from our analysis on online scraping forums, we designed 5 tasks, 3 of which you've already seen in the demos. And they represent the challenges of creating web automation programs with semantic conditions. To counterbalance the learning effect of our tool as well as the task difficulties, we randomized the task orders as well as the assignment of specification modes. So for the first 4 tasks, the user was assigned to use either prompting only or content highlighting only to specify their conditions. And for the final combined task, they're allowed to use both to explore. Overall, the participants found Semanticon very effective for conditional web scraping, more powerful and easier to use than writing their own script. We also found that the guided semi-automation mode was effective for human-AI coordination. And comparing the 2 specification modes, so the prompting versus the highlighting, we found a difference in perceived effort based on the content types, so whether it's image or text, as well as a trade-off between a sense of control from the user and their mental effort. To conclude, Semanticon allows users to express semantic intent via prompting and content highlighting. Users can create a web automation program with condition specification, refinement, and error handling in a continuous human-AI collaboration. For more discussion on the human-AI turn-taking and the implications of introducing machine learning models to programming by demonstration systems, please read our paper for more details. And on a final note, I am looking for internships for next summer, so if you have any opportunities, more than willing to chat after the presentation. Thank you for listening.
Do we have any questions? Looks like not right now. Let's see. I just had one about can you talk a little bit about what the best baseline tool, I guess, for this system is, and how does that compare to the usage of Semanticon?
Yeah, I think that's a great question. To be completely honest, I don't think there is a perfect baseline tool to compare both the program synthesis aspect as well as the content filtering aspect. In the previous slide, I showed a couple of research tools that do have capabilities for the users to record and replay and have some modifications on the processes of the automation program. So that could be a good baseline to compare the aspect of actually automating the program. And for, I guess, the content filtering, I think the best baseline would be all these big and great models that are out there, with prompting for creating artwork or prompting to create code, all of these, as well as just image recognition models in general. But I think that's not the focus of our project. It's kind of bring the good things from both sides in the system to allow users to leverage both program synthesis as well as machine learning techniques. Yeah.
Cool, thank you. I think we'll go ahead and present the award. So this paper also won honorable mention best paper award. So congratulations. So next up, we have a paper called Exploring the Learnability of Program Synthesizers by Novice Programmers. And Danya's going to present that. And the co-authors for this work are Justin Lubin and Sarah Chasins.
Hi everyone, my name is Danya Jayagopal and I'll be presenting my paper on exploring the learnability of program synthesizers by novice programmers. I also wanted to acknowledge the equal contribution of my mentor, Justin Lubin, who's also here today. So I'll go over some of the motivation for this study. Novice programmers face a lot of challenges in early programming experiences, whether this comes in introductory CS classes or outside of educational context. So in class settings, early challenges can lead to high dropout rates, and outside of class settings, they might simply drop the attempt to use automation to meet their needs. In the last few years, modern program synthesizers have progressed a lot. They now deliver on their promise of lightening the burden of programming by automatically generating code. This has led many people to hypothesize synthesis might have a role to play in some of these introductory CS classes. However, there's little research on how to make a lot of these systems learnable, and this goes for seasoned programmers as well as novices. To start making learnable program synthesizers for novice programmers, we must first understand what makes synthesis-backed tools both learnable for novices and general programmers in the first place. So there's been a lot of research about program synthesis tools in HCI conferences, at UIST and other conferences, but a lot of these tools haven't been widely adopted quite yet, which led us to ask, what are the barriers? So in particular, we wondered if their learnability of these tools might be a barrier to adoption. So that leads us to our research question, which asks, what aspects of program synthesizers contribute to and detract from their learnability by novice programmers? To answer this question, we conducted observations of 22 novice programmers. Each participant participated in a Think Aloud study in which we asked them to complete tasks using publicly available program synthesizers. We chose a set of 5 program synthesizers that I'll talk about in a little bit. Each participant tackled 3 tasks per synthesizer, then participated in a semi-structured interview. Finally, we performed a thematic analysis on the results. No part of the study was intended as an evaluation of the tools, but more so an evaluation of just the learnability of program synthesizers in general. We had participants use a variety of synthesizers. We wanted a diverse set of synthesizers, so we could see a diverse set of user behaviors. We chose Blue Pencil, Copilot, Flashfill, Reggae, and Snippy, all of which are shown on the slide. There are 7 different findings in the paper grouped into 2 broader themes: tool characteristics and user behaviors. In this talk, we'll have time to go briefly through 3 of the findings. You can see that in the next slide, I have highlighted the ones that we'll cover in the talk, but definitely come talk to me if you're interested in hearing about any of the others or discussing any of the others. So on this slide, you can see that the findings are separated into 2 broader categories. So going into the first finding that we'll go over, voluntary and incidental specifications. In our paper, we define voluntary specifications as specs created exclusively as inputs to synthesizers. For instance, the Snippy synthesizer uses voluntary specifications. The user has to type 2 question marks at an appropriate point in their program in order to initiate synthesis mode, which opens up a pop-up synthesis box. We define incidental specifications as specs that are byproducts of normal tool use. For example, when users write code in their editor, the Copilot synthesizer tool suggests a code snippet that the user might want to write next. It's worth noting that this isn't just about writing code as a specification, but also about the user just providing inputs in ways that are already familiar to them. For instance, if a user is using Flashfill, you're not necessarily writing code, but you are just writing text in a spreadsheet in the same way that you normally would if you weren't trying to give input to a synthesizer. So based on our observations of participants working with these 2 kinds of synthesizers, we derived a couple of implications, one of which was that novice programmers might prefer synthesis tools where they can also complete the task using non-synthesis strategies or pre-existing expertise, such as by writing code manually. In this kind of tool, synthesizers that use incidental specifications could potentially take advantage over the ones that use voluntary specifications because users can essentially use strategies that they're already familiar with and the tools don't interfere with the user's ability to complete the task using their pre-existing expertise. So for example, one participant remarked, is there anywhere I can write the code directly? I can't find the expression I want in these suggestions. And this participant was talking about the reggae synthesizer when it gave suggested synthesis outputs, and they didn't actually want to choose any of the ones that were being presented to them. Another participant tried to write code rather than provide input-output examples, and this was also this was in Snippy, and they said, oh, I'm sorry, I thought I had to write the code directly in the box. Let me try enter an example instead. So here, once they had entered synthesis mode, they thought that they could write code within that synthesis mode when actually the tool or the synthesizer was looking for input-output examples to use as a specification for the synthesizer. Moving into the next portion of the talk is going to go into the second finding, which was about triggerless and user-triggered initiation and result communication. So this study helped us categorize synthesizers into 4 different quadrants based on 2 important axes. So one of the axes was what triggers a synthesizer run, and the other was what triggers the display of synthesis outputs. Each of these axes had 2 different categories. The first was triggerless. In triggerless, the tool decides when to run synthesis and when to communicate results, whereas user-triggered is when the user decides when to trigger synthesis as well as when to trigger results. So on this slide, you can see essentially the categorization of the different tools, and Blue Pencil, which is marked on the slide, uses triggerless synthesis initiation and user-triggered communication. So the synthesizer here, if you can see on the slide, runs in the background without requiring any specific user action to actually get the synthesizer to run, but the user has to click on the contextual light bulb icon, which is very small but on the slide, in order to actually view the results that the synthesizer has come up with based on the code that they've already entered in. Among other results, one of the implications that we noted was that user-triggered synthesis allows novice programmers to maybe construct incorrect theories about when they should trigger synthesis. So designers of user-triggered synthesizers might want to consider identifying misconceptions about their tool via user studies. One example was the user belief that larger specifications might lead to improved synthesis performance. So this was a misconception that we found when watching users use some of these synthesizers. So designers might want to identify some of these misconceptions and then refine their tool proactively to combat them. One example of a participant having such a misconception was when they remarked, I wasn't sure when to stop adding examples because I thought I had to add one for every possible input. So this participant was using Reggae and was trying to add as many inputs as possible before actually manually triggering synthesis by pressing a button that read synthesize. And they continued to add a lot of inputs to try to have make them be as exhaustive as possible when that wasn't necessarily the best approach to getting synthesis to work. Before moving to the next slide, it's worth noting that we did find evidence to corroborate the idea that smaller specification sizes might be preferable to novices. It wasn't as large of an observation as some of the other results from our study, and this was a little bit surprising given how much this finding was emphasized in pre-existing literature. So just something we noted when going through some of our findings. Moving on to the second portion of the results about user behavior. Going back to this, the first, or I guess the only section of this portion that I'll go over is about what kind of specification does my synthesizer want, which is kind of a question that users were asking when trying to use some of these synthesizers, and we were analyzing their behavior. So we found that participants were unsure of what kinds of specifications were required by synthesizers. So the first quote on the slide was by a participant who is using Copilot. So after typing a little bit of code, Copilot produced some synthesized suggestions, but the participant didn't think that any of the results that the synthesizer had produced were actually correct. But they could not figure out how to get new suggestions or what they were supposed to do in order to get the suggestions to refresh. So that was kind of the context of the first quote. with Blue Pencil, a participant said, it feels like the light bulb pops up randomly. They were communicating that they weren't really sure which of their actions while programming or completing the task were contributing to the synthesizer to actually get run in the background, since, as we mentioned before, it was a triggerless synthesizer, so the synthesizer was running in the background without the user having actually done anything specific to, I guess, the task. So participants also noted a lack of feedback upon synthesis failure. Some quotes listed were of participants asking, is there a way to check why it failed? Do you know why it didn't work before? The latter quote was said by a participant after they seemingly entered the same thing twice on Snippy, but the synthesizer worked the second time but failed the first time. So they were confused on why the synthesizer was working with the same input one of the times, because it wasn't obvious as to why the synthesizer had failed and didn't communicate anything in the context of feedback. So from our observations, we gathered that it might be helpful for a synthesizer to have feedback about why a synthesis run has failed, as well as some documentation to help users understand why incorrect synthesis outputs were produced based on the examples that the users might have given. So just offering a little bit more context and transparency into the outputs of these synthesizers could be helpful. So here is the same slide from the beginning of the presentation with all of the findings. We didn't have time to go over the 4 findings highlighted, but the paper does go into much more depth about the ones we discussed in this talk, as well as the ones that we didn't get a chance to touch on. So please do find me if you'd like to chat about any of these. But with that, here's a little summary slide, and I'd love to take any questions.
Looks like we have a couple questions.
Jasper Chan-O'Leary, University of Washington. Super
Nice to
cool
meet
talk.
you.
It's really cool to
Thank
see
you.
qualitative work on the use of synthesizers.
Yeah.
So it seems like the talk kind of talks about characteristics of the tool that were confusing to participants, but the framing was on their use in like intro CS courses. So I'm curious if you saw like what from the findings did you see about participants' ability to actually learn from the code that was synthesized, and like maybe it was helpful or like not helpful.
Yeah, definitely. I think of these 7 themes, some of the ones, or I guess maybe the one I thought was most interesting in terms of participants learning from these activities was the last one, where we're talking about more effort and less trust is equal to more engagement. So that section is basically just talking about the fact that when users are using these program synthesizers and they get code outputted, they don't necessarily trust it as much as they might trust like a solution provided to them by their teacher in class, because if they're being provided solutions in class, they're pretty sure those are probably correct, but the ones they're getting from these synthesizers do depend on whatever input they're giving into the tool, and so there's a little bit less trust in the actual code, and also a little bit more attention being given to what they did that actually outputted the code. So we thought that there might have been an opportunity there for users to engage more with what they were seeing. So for example, when maybe a user was using Copilot and they like got back a program, we noticed that some of the participants were reading through the code and were kind of vocalizing, yes, like this makes sense, or no, this doesn't really make sense, and I need to try something else. So we were able to see some of the participants kind of vocalize their thought process about like going through the code and understanding whether there were accurate or inaccurate solutions to the tasks. And so there was an opportunity there, we felt like, for increased engagement with the tasks and just generally learning programming.
Thank you.
Yeah.
Thank you. I think that's all we have time for. So
Sounds
we'll
good.
switch to the next speaker. Cool, so the next paper is called Concept Annotated Examples for Library Comparison. And Wei-Tao Yan is presenting it along and has co-authors of Miriam Kim, Bjorn Hartman, Tianyi Zhang, and Elena Glassman.
Hello everyone, I'm Wei-Tao Yan, and today I will be presenting concept annotated examples for library comparison on behalf of my co-authors. Library selection tasks are common across many programming domains. Most of programmers search online and review documentation, blogs, Q&A posts to compare libraries. The library comparison websites such as StackShare, LayPoint, and SourceHub, etc. mainly present high-level summaries of libraries' features and community support. Vegas et al. Identified 4 factors that programmers will look at when comparing libraries: fit for purpose, size, complexity, and usability. From the variation theory, we learned that showing multiple examples in parallel can help learners develop more robust, accurate inferences about what features and feature values are and uncritical to the concept the examples are drawn from. However, if we only show multiple examples in parallel, it's still hard to compare many examples at scale. So, from the analogical learning theory, we learned that highlighting analogical concepts across examples can help learners infer more robust, accurate mental models of the latent structure of the concept the examples are drawn from. Based on both theories, we hypothesized that rendering concept annotated code examples from different libraries side by side can help programmers better understand the library similarities and distinctions, as well as make more robust, appropriate library selections. We set 5 design goals based on prior work. First, we need to help users inspect concrete code examples. Second, we need to help users compare the functionalities and their associated syntax. Third, we need to help users assess how easy it is to use each library. Fourth, we need to help users anticipate the size of the code they need to write when using each library. And finally, we need to help users discover the functional and syntactic similarities and differences between multiple libraries, as well as some notion of their respective typical usage from the distribution of code examples present in the collection. Based on these 5 design goals, we propose a novel interface prototype, PairLib, to evaluate this hypothesis. The data we used to implement the PairLib was manually collected and labeled. Currently, there are 50 code examples for each library in PairLib. Let's quickly look at how the features of PairLib reflect these design goals. The code example view shows many examples from each library side by side. Users can scroll downward in any library columns to review more examples. To better help users compare functionalities, we designed a concept hierarchy that shows all functionalities and their distributions in a single view. Each column represents the library, and each bar represents the number of code examples in each library collection that include that concept. Each concept label is assigned a unique color. PairLib highlights conceptually analogous code segments across all examples from all libraries with the same color. Third, by looking at the number of functions, variables, and styles in the code examples, users can assess how easy it is to use each library. For example, when using these three libraries for lemmatization, NLTK requires more function calls and variables compared with the other two libraries. By looking at the distribution of the number of lines in each code example, which is rendered for the design goal number 4, users can compare the size of code examples using each library. And finally, the show common substring features helps users understand the similarities and differences and the typicality of the examples. We conduct a within subjects user study with 20 participants to evaluate PyLib's effectiveness. We select 2 libraries comparison tasks from NLP or visualization domains respectively. In the NLP domain, participants were asked to compare NLTK, TestBob, and Spacey. In the visualization domain, participants compare D3.js, chart.js, and recharts. For each task, participants were asked to rank each library along 5 independent factors: fit for purpose, size, code complexity, usability, and appropriateness for a specific scenario. Then we asked the participants to list the library similarities and differences. The user study result shows that when using PyLib, participants made more consistent and suitable library selections. They also provide 6 times more comprehensive insights into similarities and differences in library support functionalities. For example, one participant successfully summarized the similarities and differences among 3 visualization libraries and provide a lot of details when using PyLib. She described that Richard is HTML-based and chart.js is CSS-based, and D3 is attribute-based. I personally find Richard's HTML-based very chunky and difficult to keep track of, as HTML syntax can be needlessly pedantic with various types of brackets. After each task, we also collect their confidence in their library selections and comparison with PyLib versus online search. And we found that participants using PyLib feel more confident about the library they choose. During the user study, participants provide many great cores. We select several cores that reflect our design goals. One participant mentioned that PyLib provides many examples for each concept, which saves a lot of time, which is related to our design goal number 1. For the design goal corresponding to the functionalities, P4 said, PyLib gives a great visual interface to systematically summarize and compare functionalities across different libraries. P16 said that PyLib compares the different usage of libraries, and we can see which library is easy to use. This reflects the design goal for usability. P5 specifically mentioned his preference for visualizing the size of code, which provides valuable evidence for design goal number 4. P18 mentioned that showing code examples in the same view helps him easily understand the similarities and differences, which correspond to design goal number 5. We would also like to mention that PyLib is a tag probe to test our hypothesis about the value of many concept annotated examples presented side by side. In the future, we want to build a tool that can can provide better support for experts by creating concept hierarchies and annotating individual code example snippets with the concepts they instantiate. And finally, the goal of such tools should be the most appropriate as a complement to existing methods for finding documentation online, like online search. To sum it all up, our work has three main contributions. First, a theory-backed conceptualization of how large collections of concept-annotated code examples present in parallel can support library comparison and assessment. Second, we design and implement a novel prototype that concretizes this conceptualization. And finally, within SIGCHI user study that demonstrates the value of concept annotated code examples side by side. Thank you so much for being here, and I'm happy to take any questions you may have.
Hi, Jeremy Warner from UC Berkeley. So great talk. I have a question. One other attribute that users might care about is like the performance of a library. So it looked like a lot of the things you're considering was like, what is it like as a user to write code or work with the library? But I was curious if you had any analysis on like, oh, like is one library faster or support like a different format of data? I guess it depends on the domain a lot, but I'm curious if you explored that at all. Thanks.
Yeah, so the question is about the four factors that we studize for like functionality, usability, complexity, etc. and size. Is not about like, we cannot include all of the factors. And from Vega's paper, they identified that 26 factors and in three categories, like technical factors, human factors, economic factors. We only study these four factors all from like technical factors because currently the library comparison website provide many support for the like human factors, economic factors, and some support for functionality. But none of them really support for like the comparison at the level of code. And yes, definitely there are many great factors that we also want to provide the comparison, such as you just mentioned performance. And yeah, this work is like it's a beginning, and we want to in the future we want to expand this work into like to cover more factors. And yeah, so that's my answer.
Hi, April from University of Michigan. Very interesting work. I have a question about like nowadays there are some like collection or like website that helps you identify like same set of data set for the same purpose. I'm wondering like if how much of the design of this library comparison can be used to like compare different data set. And I'm wondering about your insight.
Yes, definitely. This work could be potentially be extended to many domains, including what you just mentioned, like a different data set. And my imagination would be that for data set, we could show many data with like concept annotating, for example, like image data, for example, like all of this, some part of the images all belongs to like a cat, describe a cat, and the other one is like a dog. So they will like, maybe there will be a tool in the future that could support labeling the parts why the, how to identify the different concepts in this data set. And also like in other domains, like article, present many articles side by side and also annotating it with the different concepts or ideas of this article. Those articles could also be very helpful in the future with model design. Yeah.
Thank you. Let's thank the speaker again. And first software development kit for creating social robots. And Patricia Alves Aguirre is the speaker, and the co-authors are Kai Mihata, Raida Karim, Aline Bjorling, and Maya Kaikmak.
Thank you for the presentation, Amanda. And thank you everyone for sticking around. I'm going to introduce robots after such a beautiful lineup of talks we had so far. So this work directly contributes to the field of human-robot interaction, where we get to design robots like this one. And specifically, I'm going to focus on social robots, which are robots that can have meaningful connections with humans. So if we think about robots, they're basically everywhere, right? Everyone heard about them, but they are also nowhere to be found. And why is that exactly? Of course, that robots are hard to deal with, but there are some common limitations in the field of social robotics that are consistent. One of them is the lack of personalization that current social robots have. And by that I mean it's very hard for a user to customize a robot to their own needs. They are, of course, expensive, and they require specialized tech. So for someone to really buy a robot and play around with it, usually there needs to be someone else, which is an expert, like a programmer, to debug or to just help out setting everything. So what we are proposing with this work is a low-cost, flexible, and user-friendly social robot kit that addresses some of the challenges that I mentioned before. If you want, you can scan this and just keep up on the demo with me, but if not, that's also fine. What I want to mention here is that this work encompasses both an open hardware for a robot and an open software for a robot. The open hardware was published at this last year, and today I'm going to focus more on the open software part. But you will hear me talk about the hardware too, because things are so related. So before I jump into that, I want to take a step back and just look at how social robots of today look like. And these are 3 examples of very common robots that exist, and I wonder if you can think of some common design features that they have. So I would say they are of white color, generally speaking. Their outer shell is mainly made of hard plastics, not allowing for different types of touch in the interaction, and generally they are not customizable. So these robots are what you see. This has led some disruptive social robot design to emerge, some of which has also been demoed here at UIST. But thinking about some of these here in the slides, there is the Blossom robot, where everyone can actually knit their own robot embodiment and make this robot look like the way you want. There is the YOLO robot, which is a very abstract robot that resembles a creature, and even robots made of natural materials such as wood, like the Ranger robot here. So this means that actually there is an unlimited space for social robot design. And if we look at that space and consider this yellow circle as the limited space for social robot design, we can see that current social robots already exist in some of these features here. So they are humanoids, they are of white color, they have hard plastics. And then the disruptive social robots also fill in some other parts of this space. They have abstract shapes and they have soft covers, but actually this space is so big and can be made by each one of us that is very unlimited to predict how it could be. So the goal of this work is to enable anyone to create a social robot without having to purchase a specific hardware platform and without having to learn and install complex software frameworks. So the platform that I'm going to talk about today more specifically is overviewed here, and I'm going to demo you some parts of it. For more details about it, you can see the paper, but I'll just show you some of the functionalities that I think are really interesting. So what we can start by doing is really to create content for our robot. So we want to create behaviors and expressions for our robot to be able to interact with other humans. So in this tool, you can, for example, design the face of a robot and an additional interaction modality. So let's try to look at how we would design a face. So this is a web-based tool, and if you want to design a face for a robot, you would enter the face editing panel, where you have previously designed faces in this row, and then you always have a face preview where you can see the output of what you are creating at all times. You can name your different faces and input them into this library. So we could start by creating one face based on a previous one. And I've just chosen this yellow face here. And you can change different things in this face. So you can look at the binary parts of it. Does it have eyes? Does it have pupil? Does it have a mouth or not? And so you can just click the button for that. And then you also have a wider range of definitions you can choose from, such as the distance between the eyes that you can change along the slider. You can choose where the actual pupil of the robot is, or even how wide the mouth is, among many other features. In total, there are 28 features. So to represent how flexible this can look like, we recreated faces of existing social robots that are in the consumer market. So for example, you can see on your top left side the new robot from Amazon called Astro, and right next to it there is a face reproduced by our tool. Cosmo robot, which is in the bottom right, it's also a very well-known robot, and the faces of it were reproduced by the tool. So this allows researchers to, for example, make replication studies in a low-cost manner. So if we think about another output device, and we can think about a robot with a face and a belly consisted of a tablet, we can also have different ways to communicate with people by having templates already made that it's very easy to choose from. So we can, for example, ask a question and have a set of buttons that the participants can choose from. And these buttons are very easy to make, and you can instantly see how they would look like in your robot. So besides the buttons, you can also have other ways to communicate with the users. You can, for example, add a slider, and that could be more easy for children to interact with robots, as they just need to slide through the interface. You can even go more creative and change the colors or import images that you might want to add on to the conversation to make things more interesting in light, such as sending hearts to someone. So the second thing we want to do is to render this content on the robot. And you can do that by rendering it on a computer, on your smartphone, or in a physical robot. It really depends on what you want to do. And I'm going to show you a couple of ways our study participants decided to do this. So in the top left side, you can see a participant that made this Christmas type robot just using the face. Compared to the bottom right one, where the participant used the two screens for the robot. So it can have different levels of complexity. You can also add this to an existing robot, such as the top right figure. It's the fetch robot added with the face of our platform. And then you can control the robot in two ways. You can use a teleoperation style, or the robot can run autonomously. So if you decide to control the robot using a Wizard of Oz, which is a technique that is commonly used in the field of human-robot interaction, where the wizard is in another room teleoperating the robot, and the participant might know or not about this. So this is how the wizard interface would look like. The wizard would choose a face for the robot, and then would choose another belly screen, if that's the case. I'm just rendering it on the web browser because that's what I have now, but you can see that anything that the wizard would change would also change for the participant. In case of a physical robot, you can also change the motors, which means the robot would act in space and move around. If you want the robot to run autonomously, and if you are a more experienced programmer, you can actually build your own programs for the robot too. So you can come here to this part of the interface and then use a program someone else has made before, so if you don't want to start with scratch. But if you do want to start just as a blank page, we kind of make it very easy because we have a list of all the functions that you can call to program your robots. So this really serves different purposes depending on the intention. We have studied this across a lot of different case studies, totaling 64 participants overall. And I just want to mention that these are very different types of studies. Some of them are controlled experiments, some of them are participatory designs. They also include participants with different level of programming experiences, from children of 6-year-old to adults or teenagers. And they resulted in publications or just outreach, or were part of outreach activities. So for the purposes of today, I'm going to focus just on 3 examples, and the rest you can see in our paper. So the first example was made during COVID, and we made our platform available to teenagers that would create their own robots using their own personal smartphone. So here you can see that they not only created different faces for their robots, but also they created different outlooks, different embodiments. So we have a robot attached to an umbrella, or a robot in a desk full of post-its for the homework, or even in a speaker. And this is a good usage of the robot across a smartphone. We also performed a study towards mental health, where we created a robot that would provide exercises of relaxation to participants to decrease their levels of stress and anxiety. This robot was deployed in a web browser for 2 weeks in the homes of younger adults. And they would just interact with the robot every day. This is a good example of a robot deployed in this web format, and also of a controlled experiment type of study. The last study is where we actually blended things with the hardware, with the open hardware. Our open hardware consists of a core that people can just attach things on and move in different ways. So you can see here different types of robots, but they all come from our open hardware. And so you can see that the interactions can become more complex if there are 2 screens. So in terms of the take-home message, what I talked today was about an open software development kit to design social robots in a very easy and economic way. There is a possibility to pair it with an actual hardware if participants want to. And I also talked about a diversity of case studies that show the potential of this platform for different studies, such as replication studies. At the more higher level, this is a great tool to enable human-robot interaction research and interdisciplinary research. Not everyone that works in HRI knows how to program or knows how to fabricate robots, but with this tool, they can just come in very easily. It's also a tool that enables rapid prototyping and testing, and it enables different levels of engagement. So seeing participants not only as evaluators of the system, but also as content creators. And that's all I have. Thank you.
Do we have any questions?
Hi, April again. Nice work. I'm curious about the programming part of the framework that you're talking about. I'm wondering about which part was, like I may miss, but which part, what is like the programming capability of this tool? Is it like just a screen, or can you actually make some parts moving, or if there is any plan to like hook to any other hardware that with programming capabilities?
That's a great question. So the robot can be programmed in any way, really, for any interaction. A couple of examples of what participants did were more sequential programming, just maybe because there was the first interaction with the tool, so they were experimenting things sequentially. But the robot can perceive also sounds. So if you think about using a smartphone for that, you can just use the microphone for sensing or the camera for sensing. We did not extend to that point yet, but it is in our future work. The users currently are interacting with the robot to buttons, sliders, or text input or time. And through that, there can be a normal human-robot interaction conducted. So the robot comes and says hi, the participant says hi by clicking a button, and it moves on sequentially like that. And I think this enables actually really rich interactions. One of them was the mental health context, where people had to breathe at the same time as the robot. So there was a very interesting symbiosis of behaviors that emerged from there too. So it can go as much as you want, but it can also stay very simple and work.
Thank you.
Thank you.
So that's going to wrap up this session. So thanks for coming, everyone. Let's thank all the speakers again. And I just have 2 reminders. One is to not forget to vote for the best talk using the QR codes on the door. And then another announcement is about the buses. They'll be leaving from the main hotel lobby area, I believe, every half hour starting at 4. So I think the first one already left, but we'll have 4:30, 5, and 5:30 buses taking everybody to the banquet. So thanks.